Hello there, and welcome to Life Beyond Seen, where curiosity gets cosy, strange places are approached slowly, and science takes the long way around before bedtime. Tonight, we're drifting toward a place that looks simple on a map, but becomes less simple the longer you look at it. A wide, dark body of water, locked between Europe and Asia. Not quite a sea in the ordinary sense, not quite a lake in the ordinary sense, and not quite willing to explain itself quickly. Tonight, we're talking about the Caspian Sea, and more specifically why scientists still avoid certain parts of it. That sounds rather dramatic, doesn't it? As if somewhere out there, beneath a cloudy sky and a quiet stretch of water, a research vessel turns off its engines, the crew goes silent, and someone in a thick coat whispers, "Not that way." And while the real story is not quite a ghost story, it is still a very interesting one, because some parts of the Caspian really are difficult to study. Some areas are risky because of geology, some are complicated because of oil and gas activity, some are hard to enter because of borders, permissions, military rules, or old industrial zones. Some places are avoided simply because the seafloor itself is not as calm as it looks from above. The Caspian Sea has always had a slightly confusing identity. It is the world's largest inland body of water, and it sits in an endorheic basin, which means it has no natural outlet to the open ocean. Water flows in, mostly through rivers, but it does not simply flow out to another sea in the usual way. It stays, evaporates, shifts, rises, falls, and carries with it the history of everything that has entered it. This southern part is especially deep, reaching more than a kilometre in places, while the northern part is broad and shallow, more like a flooded plain than an ocean basin. So even before we get to the dangerous bits, the Caspian is already a place that refuses to behave like one neat category. And that matters, because scientists like categories. They like clean labels, careful boundaries, reliable maps, and instruments that do not come back covered in suspicious mud. The Caspian does not always offer those comforts. It is surrounded by 5 countries, shaped by rivers, fed by industry, crossed by energy routes, watched by governments, and disturbed from below by forces that have been active for millions of years. It is a working sea, a border sea, a polluted sea in places, a biological refuge in others, and a geological laboratory that sometimes bubbles, leaks, shakes, and throws mud around like a tired old kettle that has been left on too long. Before we go any further, I would love to know where you're listening from tonight. Are you near the sea, far inland, beside a river, or tucked away somewhere where the only water nearby is a glass on the bedside table? And if you have ever stood beside a large body of water at night, did it feel peaceful to you? Or did it feel just a little too quiet? There is something about dark water that makes the mind slow down. It can be calming, yes, but it can also remind us that the surface is only the surface. A lake, a sea, or even a small pond can look still, while plenty is happening underneath. Rather like a sleeping cat, really. Peaceful on the outside, very busy with mysterious internal business. And if you find this gentle journey soothing, interesting, or just a comfortable way to let the day loosen its grip, I would be very grateful if you gave the video a like and perhaps subscribed. It helps this quiet corner of science reach others who enjoy learning strange things without being shouted at by a thumbnail. Around here, we prefer our mysteries served warm, with a soft voice, steady pacing, and ideally no sudden symbols. So settle in, let your shoulders drop, and allow the Caspian to appear slowly in your mind. Picture it stretching from the cold shallows of the north down to the deeper waters of the south. To the west lie the Caucasus and the old oil lands around Baku. To the east, the coasts of Kazakhstan and Turkmenistan reach toward dry plains and desert edges. To the south, Iran meets the deepest basin. Russia touches the northern waters, where the great Volga River brings in much of the Caspian's fresh water. It is a sea without a natural ocean door, but not without traffic. Canals connect it indirectly to other waters through Russian river systems, which means ships can move in and out. Though the Caspian itself remains enclosed in a way that makes every spill, every discharge, and every long-term change more important, this is the first reason the Caspian attracts caution. When a body of water has no natural outlet to the ocean, problems do not simply wash away. Pollutants can linger, sediments can store traces of old industry. Nutrients, heavy metals, hydrocarbons and waste can gather in places where currents, river mouths, depth and chemistry allow them to settle. A Caspian environmental report describes the sea as rich in living and fossil resources, home to more than 15 million people along its coastal areas, and facing a series of environmental challenges. That is the polite official way of saying there is a lot going on here, and not all of it is tidy. The second reason is that the Caspian is not only water, it is also oil country. Long before offshore drilling became a global industry, parts of the Caspian region were already known for oil, gas, bitumen and natural seepage. Azerbaijan in particular became one of the early centres of oil production, and the offshore area near Baku is famous for its long industrial history. In some places, scientists are not just studying a marine environment. They are studying a marine environment crossed by platforms, pipelines, shipping routes, abandoned infrastructure, and zones where one careless movement can become expensive, dangerous, or politically awkward. A research vessel is not a little toy boat. It cannot simply wander wherever curiosity points. It must know what lies beneath it, what permissions apply, and what hazards may be present. And then the seafloor itself adds another layer. The South Caspian region is one of the world's important areas for mud volcanism. Mud volcanoes are not volcanoes in the red lava sense. They are places where gases, fluids and soft sediments rise from below and push their way to the surface. Sometimes they form cones, sometimes they release methane, sometimes they bring up oil, salty water or bitumen, sometimes they are quiet, sometimes they are not. Geomar researchers have noted that Caspian mud volcanoes can indicate deep oil and gas reservoirs, with methane, bitumen, and oil linked to these systems. They also emphasise that geological, chemical and physical processes need to be understood for safe activity in such areas. Now, if you're trying to fall asleep, mud volcano may not sound very relaxing. It sounds like something a child would invent after being told not to combine garden soil, bath water and a bicycle pump. But in the Caspian, mud volcanoes are serious geological features. They can be useful to scientists because they reveal what is happening below the sea floor. They can also be inconvenient, because sampling near them may involve unstable sediments, gas release, difficult seabed conditions, and areas where industry already has a strong interest. In science, a place can be fascinating and still be a place you approach with great care. Sometimes the most interesting spot on the map is exactly the spot where you do not want to drop an expensive instrument without checking the insurance first. The third reason is legal and political. The Caspian is bordered by Russia, Kazakhstan, Turkmenistan, Iran and Azerbaijan, and for a long time its legal status was debated because it did not fit easily into the normal rules used for seas or lakes. The 2018 Convention on the Legal Status of the Caspian Sea created a framework for how the surrounding states manage navigation, resources, security and research. It includes rules about territorial waters, fishery zones, seabed and subsoil resources, and scientific work. Marine scientific research in territorial waters or in areas connected to biological resources, seabed exploration, or subsoil use requires written permission from the relevant coastal state. The same convention also says that research can be suspended or stopped under certain conditions, including security concerns. That does not mean scientists are sneaking around in fear, peering over clipboards and hiding behind buoys. It means the Caspian is not an open playground. A team planning a survey cannot simply say, "That patch of water looks scientifically appealing. Let's go there after lunch." They may need permits. They may need cooperation from national authorities. They may need to share data. They may need to avoid sensitive infrastructure or security zones. They may need to work with the local scientists, government agencies, or energy companies. If the research touches seabed resources, fisheries, pipelines, or national sectors, the paperwork can be as important as the weather forecast, possibly less romantic, but much more likely to determine whether the voyage happens at all. So when we say scientists avoid certain parts of the Caspian Sea, we need to be careful. It does not always mean they believe those places are cursed, poisonous, or impossible. Often it means they are not worth entering without the right vessel, the right instruments, the right permissions, the right weather, and the right reason. Science is curious, but good science is not reckless. It does not charge into a methane seep, a restricted sector, a storm-prone shallow, or an old oil field simply because it sounds good in a documentary title. Good science brings maps, backup plans, legal approvals, safety briefings, and someone who knows how to fix a winch at 2 a.m. without becoming philosophical about it. There is also the matter of what we can see from a distance. Modern researchers no longer need to place a boat in every difficult area to learn something about it. Satellites can detect surface slicks. Remote sensing can monitor changes in water colour, algal blooms, coastline shifts, and sometimes signs of oil pollution. Acoustic surveys can map the seafloor. Historical data can be compared with new measurements. Drifting instruments, remotely operated vehicles, and carefully planned sampling stations can reduce risk. In other words, scientists may avoid entering a place directly while still studying it from above, beside it, or through data gathered at its edges. Avoidance does not always mean ignorance. Sometimes it means using a longer arm. Still, there is something quietly powerful about the fact that parts of the Caspian remain difficult. In a world where we can zoom into streets, track storms from space, and argue with a phone about the fastest route to a supermarket, the idea that a large body of water still contains awkward, undersampled, restricted or unstable areas feels almost old-fashioned. It reminds us that the Earth is not fully arranged for our convenience. Some places are still complicated because geology is complicated. Some are complicated because history is complicated. Some are complicated because 5 countries, vast energy reserves, old pollution, rare wildlife and deep basins do not make for a simple afternoon field trip. And the Caspian has plenty of rare wildlife to think about as well. It is famous for sturgeon, for seals, for migratory birds, and for ecosystems adapted to brackish water that is neither fully fresh nor fully marine. These living systems are affected by changes in sea level, river inflow, fishing pressure, pollution, climate, and coastal development. Scientists are not only asking what parts of the Caspian are dangerous to enter, they're also asking what parts are changing faster than we can understand them. Sometimes the most urgent question is not, can we go there? But, what are we failing to measure because going there is so difficult? There is a quiet irony in that. The places most avoided can become the places most important to understand. A polluted bay, an old oil zone, a field of mud volcanoes, a politically sensitive border area, a deep basin with slow water renewal, a shallow northern shelf affected by changing river flow. Each one holds clues. Each one can tell researchers something about the sea's past, present and future. But each one asks for caution in return. The Caspian does not hand over its information neatly. It makes people work for it. Sometimes with chemistry, sometimes with diplomacy, sometimes with a very sturdy boat and a crew that has learned not to trust calm water too much. As we begin this journey, we will not treat the Caspian like a monster. That would be too simple, and frankly, a little unfair to the Caspian. It is not lurking there with a villainous plan, stroking a cat made of algae. It is a real place, shaped by real processes. It has oil fields and fishing towns, research stations and ports, storms and shallow flats, deep basins and soft sediments. It has been used, studied, argued over, polluted, protected, mapped, misread, and returned to again and again by people trying to understand it. The mystery is not that scientists avoid some parts because they are afraid of the unknown. The better mystery is that the known facts are already enough to make them careful. A quiet sea can still hold gas beneath the mud. A familiar coastline can still hide old industrial waste. A map line can still change what a ship is allowed to do. A deep basin can still move slowly enough that changes take time to reveal themselves. A shallow northern shelf can be wide enough to look harmless and still be difficult for navigation. The Caspian is full of these practical complications, not fantasy dangers, not bedtime monsters, just the kind of real-world difficulties that make scientists slow down, check the plan, and sometimes choose not to go directly into a place until the right conditions are met. So tonight, as the room around you settles and the outside world becomes a little softer, we will move carefully across this inland sea. We will look at why its geography matters, why its oil history still shapes research, why mud volcanoes and methane seeps attract both interest and caution, why deep water chemistry matters, why legal boundaries can be as real as reefs, and why satellites sometimes become the safest eyes over water that ships do not enter easily. And we begin with the simplest fact of all. The Caspian has no easy exit. It is a closed basin, holding water, salt, sediment, history, industry, and unanswered questions in one enormous bowl. To understand why scientists still avoid certain parts of it, we first need to understand the strange shape and behaviour of the sea itself, because before there are restricted zones, gas seeps, old oil fields, or uncertain depths, there is the Caspian's most basic trick. It looks like a sea, behaves partly like a lake, and keeps many of its problems close to home. The Caspian's most basic trick is that it looks open, but it is not open in the way an ocean is open. Water arrives from rivers, rainfall, groundwater, and smaller streams, but it does not leave through a natural strait into the Black Sea, the Mediterranean, or any wider ocean system. It stays inside the basin until evaporation removes it. That one fact changes almost everything. It changes the chemistry, it changes the ecology, it changes how pollution behaves, it changes how scientists plan their surveys, and it changes the level of caution needed in places that, from a distance, may look like plain water with a gull or two floating on top, doing absolutely nothing useful. The Caspian is often called a sea because it is enormous, salty, and bordered by several countries. NASA describes it as the world's largest inland water body by surface area, covering roughly 371,000 square kilometres and touching 5 countries. Its northern waters are shallow, only a few metres deep in places, while the southern end drops to more than 1,000 metres. So it is not a neat bowl with one simple depth. It is more like 3 different water bodies stitched together. A shallow northern shelf, a deeper middle section, and a very deep southern basin. For a research team, that means the word Caspian is never enough. You always have to ask, which part? The flat northern shallows, the middle basin, the deep south, the salty eastern inlets, the industrial western shore. Each area has its own problems and its own personality. This is where the phrase inland ocean becomes useful, even though it is not technically an ocean. It has waves, it has storms, it has ports, ships, fisheries, oil platforms, and long horizons. Ancient observers saw its size and called it a sea because standing on the shore, you cannot see across it. But unlike a true ocean, it has no normal connection to the world ocean. NASA notes that multiple rivers empty into it, with the Volga as the largest, but because it lacks an outlet, it loses water only by evaporation, which leads to salt accumulation. That is a very simple sentence, but it carries a lot of consequences. Imagine a bathtub where water keeps arriving, but the drain has been replaced by a warm lamp. The water does not flow away. It slowly disappears into the air, while the dissolved material it carried is left behind. Now imagine that bathtub is larger than many countries. politically divided, geologically active, industrially important, and occasionally moody. That is closer to the Caspian problem. The rivers matter enormously. The Volga River, flowing in from the north, supplies the great majority of the Caspian's inflow. A recent UNEP working paper gives the Volga about 80% of inflow, while other important rivers include the Kura-Aras, Ural and Terek systems. Around 130 rivers are connected to the main drainage basins feeding the sea. That means the Caspian is not only affected by what happens on its coast, it is affected by what happens far inland, across a drainage area that stretches through farms, cities, factories, wetlands, reservoirs, dams, roads, and old industrial corridors. A drop of water entering the Caspian may have passed through a landscape with a long human history before it ever meets the sea. It may carry sediment, it may carry nutrients, it may carry traces of agriculture, it may carry pollutants, and once it arrives, there is no easy ocean exit waiting for it. This closed basin behaviour is one reason scientists treat some areas carefully. In an open sea, water exchange can dilute some pollutants, move them into larger circulation systems, or carry them away over time. That does not make pollution harmless, of course. The ocean is not a magic bin. But in a closed basin like the Caspian, contaminants can remain in the system in a more confined way. They may settle into sediments, they may collect in low-energy bays, they may become part of food webs, they may be stirred again by storms, dredging, ship movement or changes in water level. If researchers are sampling sediments in an old industrial zone, they are not just picking up mud. They may be picking up a record of decades of human activity, sealed in layers like a very unappealing cake. The same closed nature also makes the Caspian difficult to model. Scientists cannot simply copy methods used for a typical coastal sea and expect everything to work. The Caspian's water level is not controlled by global sea level in the same way the open ocean is. It depends heavily on the balance between river inflow, precipitation, evaporation, and human water management. The UNEP paper describes it as a closed basin with no natural outflow, with an average level around 28 metres below mean sea level and with continuing fluctuations. That means the Caspian can rise or fall for reasons that are partly regional, partly climatic, and partly human-made. For scientists, this creates a moving target. A shoreline studied 20 years ago may not be in the same place now. A shallow sampling station may become mudflat. A port channel may need dredging. A bird nesting area may shift. A seal breeding area may be affected by changes in ice. This is not just a slow background issue. Measurements and projections show that the Caspian has been losing level in recent decades. A 2023 study in Communications Earth and Environment reports that satellite altimetry showed a decline of about 1.5 metres between 1996 and 2021, with a faster decline after 2006. The same study projects that continued warming could cause additional sea level decline by 2100, with major ecological and economic effects. So when researchers decide where to go, they are not studying a stable water body that politely stays the same between visits. They are studying a system that is changing while they watch it, and sometimes faster than infrastructure, maps, and old assumptions can keep up. The northern Caspian is a good example of why the closed basin matters in practical terms. It is shallow, broad, and heavily influenced by river inflow. NASA describes the northern part as only about 5 to 6 metres deep, while the southern end is far deeper. In shallow water, small changes in sea level can create large changes in coastline. A 1 metre fall in a steep rocky shore may not move the shoreline very far, but in a flat, shallow area, that same fall can expose wide areas of seabed. For scientists, this can turn yesterday's boat route into today's grounding risk. It can leave instruments stranded. It can change where fish spawn, where birds feed, and where sediments dry out. It can also make access more expensive, because boats need safe channels, and safe channels may need constant checking. The northern shallows also receive much of the incoming fresh water, so their chemistry can differ sharply from other parts of the sea. Britannica gives the Caspian's average salinity at about 12.8 parts per thousand, but near the Volga outlet it can be as low as about 1 part per thousand, while the Karabogaz-Gol area can reach far higher salinity because of intense evaporation. This is another reason scientists cannot treat the Caspian as one simple water mass. A sample from the north and a sample from a salty eastern inlet may tell very different stories. Instruments calibrated for one set of conditions may need adjustment in another. Species that survive in one region may not tolerate another. Even basic questions like how dense the water is, how it mixes, and where material settles depend on where you are. For a sleepy listener, salinity may sound like a small technical detail. It is not. Salinity affects water density, circulation, ice formation, species distribution, corrosion, and sediment chemistry. It affects how water layers mix and how oxygen moves downward. In a closed basin, salinity is also a clue to the long struggle between inflow and evaporation. Fresh water enters, evaporation removes water, and salts remain. If river inflow declines or evaporation increases, the balance changes. If the water level falls, shallow habitats shrink. If salty areas become more isolated, they can become even saltier. It is a slow process in some places, but it is not imaginary. It is measurable, and it matters. The eastern side of the Caspian gives one of the clearest examples of evaporation's power. Karabogaz-Gol, sometimes described as a bay or lagoon on the Turkmenistan side, is extremely saline because water enters and then evaporates intensely. This is not the place for a casual swim, unless your idea of relaxation involves becoming lightly pickled. From a scientific point of view, though, such areas are valuable. They show how a closed system concentrates minerals and salts. They also show how small changes in connection, water level, and evaporation can transform a place. But they are not always easy areas for routine research. High salinity can damage equipment. Shallow waters complicate navigation. The surrounding terrain may be remote. The value of the data has to be weighed against the difficulty of getting it safely. The closed nature of the Caspian also affects pollution research. When pollutants enter from rivers, coastal cities, ports, industrial sites, or oil operations, scientists need to know where they go. Do they remain dissolved in the water? Do they attach to fine particles and sink? Do they collect in river deltas? Do storms resuspend them? Do organisms absorb them? In a system without an ocean outlet, these questions become more urgent. A contaminant may not disappear from the Caspian just because it leaves the surface water. It may move into sediment, then into bottom-feeding organisms, then into fish, then into birds, seals, or people. This is not a dramatic monster story. It is a practical environmental pathway. The kind that makes researchers wear gloves, label samples carefully, and avoid eating lunch too close to the sediment cores. This is one reason certain areas are avoided until there is a specific reason to enter them. A site near an old industrial discharge zone may require special handling. A river mouth after flooding may carry unstable sediments and unknown contamination. A shallow bay with poor water exchange may hold concentrated pollutants. An old dumping area may be poorly mapped. A research team may still study these places, but they will not treat them casually. They may prefer remote sensing first, then limited sampling, then more detailed fieldwork only after risks are understood. This does not mean fear is driving the science. It means the Caspian rewards preparation and punishes the assumption that water is just water. There is another difficulty that sounds simple but causes real trouble. The sea is big enough to behave like a sea, but enclosed enough to behave like a lake. That makes fieldwork awkward. Weather can change quickly. Waves can rise. Storms can be serious. Yet unlike an open ocean expedition, a Caspian expedition also has to think constantly about national sectors, local permissions, and limited exit routes. A vessel may be close to land on a map but still far from the right port, the right customs point, the right emergency support, or the right permission boundary. Scientific work is not only about lowering a probe into water. It is about getting the vessel there, keeping the crew safe, recovering the instruments, storing the samples, and returning without creating a diplomatic incident, which is generally considered good manners. The changing level of the sea makes this even harder. Ports, channels, and coastal infrastructure are built for certain water levels. If the Caspian falls, harbours may become too shallow, dredging may increase, sediment disturbance may rise, ships may have to follow narrower routes, research vessels may lose access to nearshore zones where long-term data used to be collected. The UNEP paper notes that Caspian ports are vulnerable to sea level change because they are expensive, fixed in place, and built to last, while the Astrakhan connection depends on the long Volga-Caspian Canal for ships to travel between port and sea. That kind of infrastructure does not adjust easily when the water shifts. For scientists, this can create gaps in knowledge. The places most affected by falling water may be exactly the places that become hardest to reach. A shallow wetland may become mud. A former boat route may need a smaller vessel. A smaller vessel may not carry the same equipment. If ice conditions change, seal researchers may lose safe access to breeding areas. If bird habitats shift, old survey points may no longer describe the same ecosystem. Long-term science depends on comparing present measurements with past ones, but if the physical site changes, the comparison becomes complicated. It is like trying to weigh yourself every year while someone keeps moving the floor. The closed basin also means that the Caspian's problems are shared, but not always shared equally. One country may manage a river, another may receive the ecological effect. One coast may have oil infrastructure, another may have fishing grounds affected by wider changes. One area may gain temporary economic advantage from a lower shoreline, while another loses port access or wetland habitat. Water does not care about borders, but research vessels have to. This is why cooperation is so important in the Caspian, and why some areas remain understudied. Not because scientists are uninterested, but because access, data sharing, and long-term monitoring require agreement. Science can measure salt, mud, fish, and oxygen. It cannot automatically simplify politics, though many researchers would probably appreciate it if someone invented a reliable instrument for that. Because there is no easy exit, the Caspian also keeps long memories. Its sediments can record past climate shifts, old river changes, pollution history, biological changes, and industrial activity. That is scientifically useful. A core taken from the seabed can act like a timeline, showing layers deposited year after year. But long memory can also mean long responsibility. If pollutants are buried, they may stay buried until disturbed. If nutrients collect, they may change oxygen conditions. If invasive species arrive, the enclosed system may give them room to spread in ways that are difficult to reverse. The Caspian is not sealed like a jar, but it is enclosed enough that mistakes can echo. This is why researchers are careful with sampling in certain areas. Taking measurements is not always neutral. Dropping equipment can disturb the seabed. Anchoring can damage habitats or hit infrastructure. Dredging for samples can release material. Even entering shallow wildlife zones at the wrong time can disturb birds or seals. In a closed and stressed system, the aim is to learn without adding unnecessary pressure. The best field science is often less heroic than people imagine. It involves slow planning, boring forms, properly cleaned sampling bottles, risk assessments, and the quiet wisdom of not going somewhere just because the map has an empty patch. There is also the problem of representativeness. In an open, well-mixed area, one water sample may tell you something broad. In the Caspian, one sample may only tell you about a very specific place at a very specific time. A sample near the Volga is not the same as a sample from the deep southern basin. A spring sample is not the same as a summer sample. A calm weather sample is not the same as one taken after a storm. A shallow bay beside a city is not the same as a remote offshore point. This may sound obvious, but it matters when scientists are trying to make maps, predictions, and policy recommendations. Bad sampling design can create false confidence, and false confidence is one of the least useful things to bring on a research boat. The no-exit condition also helps explain why scientists use satellites so heavily. From space, researchers can monitor shoreline retreat, surface colour, sediment plumes, ice cover, and some signs of oil or algal activity. Satellites cannot replace boats because they cannot easily measure everything below the surface or collect physical samples, but they are very useful when the area is too shallow, too remote, too restricted, or too risky for regular field visits. They let scientists see patterns before deciding where to send people. In a place like the Caspian, that is not a luxury. It is often the safest first step. Even with satellites, the closed basin remains difficult because many of its most important processes happen below the surface. Water layers, sediment chemistry, bottom oxygen, contaminant burial, gas release and biological stress cannot always be understood from above. A smooth surface can hide a low oxygen bottom. Clear water can still have contaminated sediment. A quiet shoreline can be retreating year by year. A shallow area can become inaccessible before the full ecological change is documented. The Caspian often requires both distance and closeness, satellite eyes from above, careful sampling from boats, local knowledge from people who live there, and long-term records that show what a single visit cannot. So when scientists avoid certain parts of the Caspian, the first explanation is not one dramatic hazard. It is the combined effect of enclosure, shallow zones, changing water levels, salinity differences, sediment build-up, pollution history, and access problems. The sea has no easy way to flush itself clean, no simple connection to the wider ocean, and no stable shoreline that can be taken for granted. It is large enough to be dangerous in bad weather and enclosed enough to hold on to its problems. That combination makes it scientifically valuable, but also scientifically demanding. And this brings us closer to the darker practical reasons some areas are approached with caution. A closed basin does not only hold salt and river sediment. Around the Caspian, especially along parts of the western coast and offshore zones, it also holds the marks of one of the oldest oil-producing regions on Earth. The same lack of an easy exit that shapes the water and salt balance also shapes what happens when hydrocarbons, drilling waste, old infrastructure and natural seepage enter the system. The geography prepares the stage. The next layer is industry, and in the Caspian, that story has been running for a very long time. The geography prepares the stage. The next layer is industry, and in the Caspian, that story has been running for a very long time. Long before satellites watched the water from above, before offshore platforms stood on steel legs, and before engineers argued with pipelines in the middle of rough weather, people around the Absheron Peninsula already knew the ground could burn, leak, stain, and smell of oil. The Caspian Sea region is one of the oldest oil-producing areas in the world, and historical records describe primitive oil extraction near Baku going back hundreds of years. The same region later became important for the Russian Empire, then the Soviet Union, and later for the modern energy systems of Azerbaijan, Kazakhstan, and other Caspian countries. So when scientists enter some parts of this sea, they are not entering untouched water. They are entering a place where geology, industry, and history have been mixed together for generations. This is one reason certain research zones are treated cautiously. A modern scientist studying the Caspian is not only asking, what lives here? Or, how deep is it? They may also need to ask, what was built here? What was spilled here? What was drilled here? What was buried here? What old pipe crosses this seabed? What is still producing nearby? What is no longer maintained? What happened before records became reliable? These are not dramatic questions, they are practical ones. The seafloor near old oil regions can be a busy archive. It can hold natural petroleum seepage, old industrial residues, metal debris, drilling waste, buried pipelines, anchor scars, and sediments that have quietly collected chemicals for years. It is less like walking into a clean laboratory and more like opening an old garage where every shelf has a label missing. Baku's oil history is especially important here. Azerbaijan's Ministry of Energy describes the country as one of the earliest places where oil was extracted using industrial methods, with industrial oil extraction from a well at Biberheybat in 1846, the first oil refinery built in Baku in 1859, and rapid development of fields around the Absheron Peninsula during the second half of the 19th century. By 1901, Azerbaijan produced 11 million tonnes of oil, described by the ministry as more than half of world output at the time. That means the Western Caspian was not only a place where oil was found, it was one of the places where the modern oil age learned to stand up, put on its boots, and make an enormous mess before environmental monitoring had fully learned to keep notes. Now, oil itself is not unusual in the Caspian region. Some of it is natural. In places, hydrocarbons seep from the ground because the geology below is rich in petroleum systems. That creates a problem for scientists because not every oily trace has the same origin. A slick on the water, a smell in the mud, or hydrocarbons in sediment may come from natural seepage, old production, a recent leak, ship traffic, runoff from land, or several of these at once. It is a little like entering a kitchen and smelling smoke. It might be burnt toast. It might be the oven. It might be a candle. It might be your neighbour experimenting with confidence and no recipe. The smell tells you something happened, but not enough by itself. In the Caspian, researchers need chemistry, sampling and context to separate natural petroleum signals from human pollution. That sounds straightforward until you imagine doing it from a boat over an old offshore field. A team may lower a sediment core into the water, bring up a dark cylinder of mud, and then try to read its layers. The top may tell them about recent conditions. Lower layers may hold older chemical signals. Bacteria in the sediment may be breaking down hydrocarbons. Oxygen may disappear with depth. Sulfate, methane, iron, and other chemical markers may change from layer to layer. A study of Caspian Sea sediment cores exposed to simulated petroleum seepage examined how hydrocarbon flow affects biogeochemical gradients, redox processes, petroleum-degrading microbial communities, and the composition of petroleum moving through the sediment. In plain language, oil passing through mud does not just sit there politely. It changes the chemistry, feeds certain microbes, and affects the hidden life and reactions below the surface. That is fascinating science, but it is also a reminder of why some areas are not approached casually. In a clean, sandy, well-mapped place, sampling is already difficult enough. In an old petroleum zone, sampling may require safety rules for hydrocarbons, gas, unstable mud, contamination control, and industrial navigation. You cannot simply drop instruments wherever you please. A corer could hit debris, an anchor could catch old infrastructure, a survey line could cross an active pipeline route, a vessel could wander too close to a platform. Even if the water surface looks empty, the seabed may not be empty at all. Research ships are careful for the same reason you are careful when reaching into the back of a kitchen drawer. There may be useful things in there, but there may also be something sharp, sticky, or impossible to explain. One of the most famous symbols of Caspian offshore oil is Neftdashlara, often called oil rocks. Guinness World Records lists Neftdashlari as the oldest offshore oil platform, noting that construction began in 1949 and oil production began in 1951. It was not just a single platform, it developed into a functioning town in the Caspian Sea, with hotels, hostels, a bakery, a power station, and separate islands connected by more than 200 kilometres of trestle bridges on metal stilts. That image is remarkable. Not one rig standing alone, but a whole industrial settlement above the water, with roads where roads should not really be. It is the sort of place that makes engineering look both impressive and slightly stubborn. Azerbaijan's energy history places oil rocks at the beginning of offshore oil extraction in the country. The Ministry of Energy says the first offshore oil well at Oil Rocks was drilled on November 7, 1949, at a depth of 942 metres, producing 100 tonnes of oil per day, and that the commissioning of the field in 1950 began Azerbaijan's era of offshore oil development. SOCAR's history also marks 1949 as the discovery of Neft Dashlari, about 40 kilometres offshore and 90 kilometres from Baku. This matters because the Caspian was not simply copied from later offshore oil regions. It was one of the places where offshore oil production developed early, using methods and structures from a different industrial period. Old offshore areas can create a special kind of research caution. Modern platforms are built with current standards, current maps, current monitoring systems, and clearer safety zones. Older fields may have layers of infrastructure from different decades. Some parts may be repaired, replaced, removed, buried, corroded, or poorly documented. A scientist planning to study sediment, water quality, fish, benthic organisms, or methane release near such areas has to consider both the natural environment and the industrial footprint. The danger is not necessarily that the whole place is unsafe every moment. The danger is that uncertainty is expensive at sea. If you do not know exactly what is below, you do not behave as if you do. That is how equipment survives. It is also how people survive, which is generally the preferred outcome. This is not only an Azerbaijani story. The Caspian region as a whole has major offshore and coastal energy development. The EIA's 2025 regional analysis states that significant oil and natural gas reserves exist in offshore deposits in the Caspian Sea and onshore fields in Caspian basins. It also notes that Azerbaijan's offshore Caspian fields accounted for almost all of its petroleum and natural gas production in 2022, while Kazakhstan was the second highest petroleum producer from offshore Caspian fields. In the same report, offshore Caspian production from the covered regional countries accounted for over 1 million barrels per day of petroleum and over 4 trillion cubic feet of natural gas in 2022. Those numbers make it clear that the Caspian is not a quiet scientific pond with a few old stories attached. It is an active energy region. Active energy regions are hard places for independent science. Not impossible, but hard. There are security rules. There are commercial sensitivities, there are safety distances, there are pipelines and production areas, there are ships moving for work, not research. There may be restricted zones where entry requires permission, scheduling, escorts, or coordination with operators and authorities. Even when everyone cooperates, a research survey near oil infrastructure can become a complicated dance. The scientists want clean data, the operators want safety, the government wants rules followed. The sea wants to do whatever the sea was going to do anyway. Somewhere in the middle is a vessel full of people trying to keep a sampling schedule, while the weather looks at them with mild disrespect. The environmental concern is not imaginary. The State of the Environment report for the Caspian Sea notes that oil pollution incidents are a real potential danger in the region. It also warns that, because the Caspian is closed, spills have the potential to cause considerable harm to seawater life and shorelines, and that even small leaks can have a large impact. The same report identifies oil pollution hotspots along the Azerbaijan coast, where many old oil facilities exist. This does not mean every oil area is a disaster zone. It means that in a closed inland sea, the margin for careless work is smaller. A leak does not simply vanish into the Atlantic and become someone else's modelling problem. The sediment record also matters. The same State of the Environment report describes petroleum hydrocarbon findings from Caspian monitoring, including petrogenic signals at some sites in Azerbaijan, Kazakhstan and Russia, and high concentrations of oil products and phenols in Baku Bay and the coastal area of Sumgayit in a 2009 monitoring survey. It also notes relatively high oil hydrocarbon concentrations around the Satpayev oil field and the seaport of Bautino. For scientists, those kinds of findings shape field decisions. A polluted or suspected polluted area is not ignored, but it is approached differently. Sampling plans may need contamination controls, protective handling, careful storage, and methods that can distinguish old pollution from new inputs. Baku Bay is a good example of why the Caspian's oil history cannot be separated from urban and industrial history. A bay beside a major city is not affected by one source alone. It may receive signals from shipping, wastewater, old industrial sites, storm runoff, port activity, and coastal construction, along with oil-related sources. When scientists look at such a place, they are not reading one clean sentence. They are reading a page where several people have written over each other in different ink. A hydrocarbon measurement may not be enough. They need patterns, they need ratios, they need metals, organic compounds, grain size, oxygen conditions, current patterns, and time series. Otherwise, the data can say something is here without saying clearly where it came from. This is where caution can look like avoidance from the outside. A viewer looking at a map might wonder why scientists do not simply send more boats into the old oil zones and take all the samples anyone could want. But every sample has a cost, every station has a risk, every restricted or industrial area adds paperwork, every contaminated sample requires proper handling, every instrument lowered near infrastructure carries consequences if it becomes tangled, lost, or damaged. Science is not just curiosity in a waterproof jacket. It is logistics, responsibility, and a budget that usually does not enjoy surprises. There is another reason old oil fields are scientifically difficult. The environment may have adapted in uneven ways. Microbes that break down hydrocarbons can become active in petroleum-affected sediments. Some benthic organisms may avoid contaminated areas. Others may tolerate them. Fish may move through rather than stay. Pollutants may not remain at the surface but may settle into fine-grained sediments. Storms can disturb those sediments and move material again. A single visit may miss the pattern. A calm week may show one picture. A storm season may show another. A hot summer with low oxygen may change the chemistry. The Caspian often requires patient monitoring, and patient monitoring near industrial zones is never as simple as placing a chair by the water and waiting with a notebook. Then, there are the older coastal oil lands. Grida Rendell's Caspian hazard material notes heavy oil-related land pollution around parts of the region, including about 30,000 hectares of the Absheron Peninsula, polluted by oil products and industrial waste, and much larger areas in Kazakhstan's Atirau and Mangistau regions affected by oil pollution in soil. Land pollution matters to marine science because rain, groundwater, rivers, wind-blown dust, and coastal erosion can move material toward the sea. A shoreline is not a wall, it is a meeting place. What happens on land can become a seabed question later. In some areas, scientists also have to think about old wells. A well is not just a hole, it is an engineered pathway into the subsurface, and if it is old, damaged, poorly sealed, or poorly documented, it can become a point of concern. Modern well abandonment has procedures, but older industrial histories are not always neat. Around the world, researchers studying old oil provinces often worry about leakage pathways, seabed disturbance, and the condition of aging infrastructure. In the Caspian, where offshore activity began early, and where some facilities have been exposed to decades of waves, corrosion, storms, and changing sea levels, that concern becomes part of the background. A scientist does not have to assume the worst. They only need to admit that old and underwater is a combination that deserves respect. The Caspian's falling water level can also complicate old oil areas. A structure built for one shoreline or water depth may behave differently as the sea retreats. Shallow approaches can become harder for vessels. Old coastal contamination can become exposed. Formerly submerged surfaces can dry, crack, or be disturbed. Ports and terminals may need dredging, and dredging can disturb sediments that have been quiet for a long time. So the oil field does not simply sleep beneath the waves in a stable way. The waves themselves move away in some places, and that changes what is covered, what is exposed, and what can be reached. There is a human side to this as well. Oil platforms are workplaces, terminals are workplaces, ports, service vessels, pipeline routes, and support bases are part of people's daily lives. Scientists working nearby have to respect that. They are not entering an empty mystery. They are entering a working industrial landscape where people have jobs, routines, safety rules, and very little interest in a research vessel drifting into the wrong place because someone got excited about plankton. The Caspian is not only natural habitat and not only industrial machine. It is both at once, which makes studying it more difficult than either story alone. The older oil zones also show why avoid can mean delay until the right method exists. Scientists may avoid direct sampling in a hazardous area, but use satellite imagery, historical records, operator data, side-scan sonar, chemical fingerprinting, or samples from nearby safer stations. They may build a picture from the edges first. They may return later with better equipment. They may choose a smaller vessel for shallow water or a remotely operated system for a risky seabed. Avoidance can be a sign of good planning, not surrender. There is no scientific prize for losing a sensor to a rusting pipe and then writing an emotional invoice. The more one looks at the old oil fields of the Caspian, the more the word sleep becomes slightly misleading. They may look asleep from the surface, especially at night when the water is dark and the platforms become small points of light. But chemically, mechanically, and historically, they are not inactive. Sediments are still reacting. Microbes are still feeding. Pipes and metal structures are still aging. Currents are still moving fine particles. Companies are still producing in some areas. Governments are still regulating. Researchers are still trying to separate natural seepage from the industrial impact. Nothing about this is frozen in the past. This is why scientists still treat certain Caspian oil zones with care. The issue is not a single forbidden patch of water where no one dares to go. It is a chain of reasons. Old infrastructure, active production, closed basin vulnerability, possible contamination, unclear sediment histories, safety zones, legal permissions, shallow navigation, and the simple fact that oil-rich geology keeps sending signals upward from below. In many places, the question is not whether science should study them. It is how to study them without making the problem worse, risking the crew, damaging equipment, or confusing the evidence. From here, the story moves naturally downward. Beneath old platforms and long pipelines, beneath the sediment that records spills and seepage, there is another Caspian feature that makes researchers cautious. It is older than the oil industry, stranger than a rusting trestle, and sometimes strong enough to reshape the seabed without asking permission. The same underground pressure that helped create the region's oil and gas wealth can also push mud, water and methane upward through weak places in the crust. And in the Caspian, that brings us to one of its most unusual hazards, mud volcanoes and the breathing seafloor beneath them. Beneath old platforms and long pipelines, beneath the sediment that records spills and seepage, there is another Caspian feature that makes researchers cautious. It is older than the oil industry, stranger than a rusting trestle, and sometimes strong enough to reshape the sea floor without asking permission. The same underground pressure that helped create the region's oil and gas wealth can also push mud, water and methane upward through weak places in the crust. And in the Caspian, that brings us to one of its most unusual hazards, mud volcanoes and the breathing sea floor beneath them. A mud volcano is not a volcano in the usual fiery mountain sense. There is no river of glowing lava rolling down the side, no dramatic ash cloud blocking the sun. No heroic scientist standing too close with a clipboard and questionable survival instincts. Instead, mud volcanoes form where pressurized fluids, gases, and sediments move upward through the ground. They can release mud, water, methane, oil traces, salty fluids, and broken pieces of deeper rock. Some bubble gently, some ooze, some build cones, some sit beneath the sea and form banks or islands, some erupt suddenly. And because the Caspian sits above a hydrocarbon-rich sedimentary basin, especially around Azerbaijan and the South Caspian, these features are not rare little oddities. They are part of the region's basic geological character. NASA describes Azerbaijan as having at least 220 mud volcanoes, while some researchers put the number closer to 350, making it one of the highest concentrations of mud volcanoes on Earth. Many are found near Baku and Kobustan, where folds and faults create cracks that allow methane-rich mud to rise toward the surface. NASA also notes that there are at least 140 underwater mud volcanoes in the South Caspian Sea along Azerbaijan's coast, including several island-forming examples in the Baku archipelago. That last detail is important. On land, a mud volcano may be visible. It may form a cone, a pool, a dome, or a cracked patch of ground. A person can walk around it, measure it, take samples, and possibly step back if it begins making noises that seem unfriendly. Underwater, things become harder. A submarine mud volcano can sit beneath an ordinary-looking surface. The water above it may look calm. A small wave may pass over it. A gull may sit nearby with complete confidence, because gulls are famously poor at geotechnical assessment. But below the surface there may be soft deposits, gas-charged sediments, unstable slopes, or vents releasing fluids into the water column. This is what people mean when they talk about the seafloor breathing. It is not breathing like an animal, of course. It is not taking in air and sighing over the problems of being sediment. It is releasing fluids and gases from below, sometimes slowly, sometimes in pulses, sometimes through vents that shift over time. A quiet patch may begin to bubble. A mound may grow. A bank may change shape. A new mud flow may spread across the seabed. For scientists, this is fascinating because it offers a rare look into deep processes without drilling kilometers into the earth. Mud volcanoes bring material upward. They deliver chemical clues from buried layers, from hydrocarbon systems, from sediments that would otherwise remain hidden. But that same usefulness is what makes them awkward. They are windows into the subsurface, but the windows occasionally spit mud. The South Caspian Basin is especially suited to this kind of behaviour. Studies of offshore Azerbaijan using seismic data have found high concentrations of mud volcanoes in the southern part of the study area, linked to subsurface structures. Some low-relief mud volcanoes are only several tens of meters high, while larger ones can have relief greater than 200 meters. The same study links their formation to faults, compressional tectonic forces, overpressured sediments, high sedimentation rates, and hydrocarbon generation. In plain language, the basin has thick sediments, underground pressure, faults, and gas-rich systems. That is a good recipe for mud volcanoes, and not a good recipe for assuming the seabed is politely flat. Imagine, just for a moment, lowering a scientific instrument into water that looks simple from the deck. Perhaps it is a corer, designed to take a neat sample of seabed mud. Perhaps it is a camera frame, a gas collector, or an acoustic device. The crew has checked the coordinates, the weather is acceptable, everyone is wearing sensible clothing. Then the instrument reaches the bottom, and the bottom is not quite the bottom you expected. It may be softer than predicted. It may be uneven. It may have gas pockets. It may be covered by fresh mud flows. It may be near a vent. It may be close to an old structure. Because in the Caspian, geology and industry have a habit of occupying the same neighbourhood. Suddenly, the simple act of taking a sample becomes a negotiation with mud, pressure, cables, currents, and the uncomfortable possibility that the equipment may come back smelling like the inside of a fossil fuel's diary. Geomar researchers have described Caspian mud volcanoes as scientifically important because they can be sources of greenhouse gases, natural hazards, and indicators of oil and gas reservoirs. They note that gas venting from mud volcanoes may contain up to 90% methane, that methane is flammable, and that bitumen and oil can be sampled from mud volcano cones. They also point out that Azerbaijan was one of the first countries to develop oil production in an area of active mud volcanism, which means the geological and industrial stories are closely tied together. Methane is one of the key reasons scientists approach these places carefully. In normal conversation, methane may not sound especially dramatic. It is a gas. It is invisible. It does not have the instant visual flare of a thunderstorm or a collapsing cliff. But methane matters for several reasons. It is a greenhouse gas. It is flammable. It is connected to petroleum systems. It can feed microbial communities. It can form bubbles in sediment. It can move through faults and fractures. When it escapes from the seabed, it can affect water chemistry and can sometimes be detected acoustically as bubble streams rising through the water. In some settings, methane can also be linked with gas hydrates, those ice-like compounds that trap gas under certain temperature and pressure conditions. The Caspian is not simply a flat pan of water. In places, it is a pressure system with leaks. There is a tempting way to imagine this, as though the Caspian seabed is a sealed lid and methane is knocking politely from underneath. But the reality is messier. Gas does not rise everywhere equally. It follows weaknesses, it follows faults, it follows fractures. It can move with water and mud through complex pathways. Some vents may stay active for long periods, others may pulse, some may be dormant then reactivate. Some may be connected to deep sources, others may reflect shallower processes. If scientists want to understand which is which, they need samples, maps, isotope measurements, gas composition data, seismic profiles, and long-term observation. One sample from one day is rarely enough. Mud volcanoes are not punctual employees. They do not always show up on schedule. This unpredictability is one of the reasons they are hazardous. A mud volcano may spend years looking uneventful and then erupt violently. NASA's 2026 Earth Observatory article describes mud volcano islands along the Absheron Peninsula that were born from explosive mud volcano eruptions and reshaped by erosion. It also describes Sungimyeon Island, also known as Ostrov Svinoi, as a place known for particularly violent eruptions, including a 1932 event that released a fireball about 150 meters tall and injured 13 people. NASA also notes that mud volcanoes can produce short but extremely violent eruptions, sometimes with large fireballs, and can create whole new islands within minutes. That is the sort of sentence that makes a research safety officer put down their tea and sit up a little straighter. Because a mud volcano eruption is not only a geological event, it can become a navigation hazard, a fire hazard, a sampling hazard, and a data hazard all at once. If a feature changes shape, older charts may become less reliable. If gas rises suddenly, the water column changes. If mud is released, visibility can drop and sediments can spread. If methane ignites, the problem becomes rather more immediate than a polite academic discussion. And if the eruption is offshore, people may not witness the beginning from land. The first clear sign may come from satellite images, ship reports, acoustic anomalies, or a newly formed patch of mud where yesterday there was only water. The Caspian has provided dramatic examples of this. NASA reported in January 2025 that the Kumani Bank mud volcano, about 25 kilometers off the eastern coast of Azerbaijan, produced a temporary island after an eruption in early 2023. Landsat 8 and Landsat 9 imagery showed that the volcano's crest was below the sea surface in November 2022. An island had appeared by February 14, 2023, and by the end of 2024 only a much smaller part remained above water. Additional satellite observations suggested the island emerged between January 30th and February 4th, 2023, and measured about 400 metres across. There is something almost comically inconvenient about an island that appears, makes everyone update their mental map, and then begins eroding away again. It is like the seafloor briefly raising its hand and saying, "Actually, I am land now," before changing its mind. But for scientists, this is not just a curiosity, it proves that parts of the Caspian seabed can change quickly. It shows how underwater mud volcanoes can affect the surface. It reminds researchers that some hazards are not static. A feature mapped years earlier may not look the same now. A shallow bank may grow, shrink, or disappear. A sediment plume may mark new material entering the water. A place that seemed safe for navigation or sampling may need to be checked again. Kumani Bank has a longer history as well. NASA notes that previous recorded eruptions there happened in short bursts lasting less than 2 days and produced islands of different sizes and lifetimes. One event in 1861 formed an island 87 metres across and 3.5 metres above the water, which eroded away by early 1862. A stronger eruption in 1950 created an island about 700 metres across and 6 metres high. This is not an isolated party trick. It is a repeated pattern from a restless feature beneath the Caspian. For field science, a temporary island is both a gift and a nuisance. It is a gift because it reveals a fresh eruption deposit. It allows researchers to study new material from below. It may show how mud, gas and sediment move during an eruption. It can be compared with satellite imagery to understand rates of growth and erosion. But it is a nuisance because it may be unstable, difficult to land on safely, dangerous if gas is still venting and rapidly changing under wave action. A newly formed mud island is not the sort of place where you stroll ashore with a picnic basket and an optimistic hat. It may be soft, cracked, slippery, gas-rich, and structurally unreliable. It is land in the same way a badly made pudding is architecture. This is why satellites become so useful. They let scientists observe places that might be too dangerous or inconvenient to approach immediately. A satellite does not care if the seabed is soft. It does not get stuck in mud. It does not complain about methane. It passes overhead, gathers imagery, and lets researchers compare changes over time. But satellites have limits. They can show the surface expression, the sediment plume, the island shape, the erosion pattern. They cannot directly collect gas from a vent or measure detailed sediment chemistry at depth. For that, scientists eventually need instruments closer to the source. And that is where caution returns. A muddy vent field can also complicate biological research. Mud volcanoes and cold seeps can create unusual habitats. Methane and other compounds can support microbial communities that use chemical energy rather than sunlight. In marine seep systems around the world, such chemistry can support specialized organisms, though the exact communities depend on local conditions. In the Caspian, researchers may be interested in microbes, benthic animals, chemical gradients, and how seepage affects surrounding sediments. But sampling these habitats without disturbing them can be difficult. A heavy instrument can crush delicate structures. A poorly placed anchor can damage the seabed. A gas-rich sediment core can change pressure as it is brought upward, altering the sample. The scientist wants the truth of the mud, but the mud does not remain exactly itself when removed from its home. There is also the issue of subsurface deformation. GMR describes a transition zone southeast of Baku as a high-risk area because of natural hazards such as mud volcano eruptions and subsurface sediment deformation, as well as abandoned and defunct offshore installations. That is a very dense warning. It means researchers must think not only about mud volcanoes as isolated cones, but about a broader seabed environment where sediments may shift, deform or fail, and where old industrial structures may add another layer of risk. Subsurface sediment deformation sounds dry until you imagine what it means at sea. The the seabed is not always firm ground. It can contain layers of clay, silt, sand, gas, water, and mud at different pressures. If those layers move, slump, compact, or fracture, they can affect pipelines, platforms, cables, and sampling equipment. In some places, soft sediment can behave less like stable ground and more like a very slow, very heavy material deciding where it would prefer to be. This matters for engineering, but it also matters for science. A benthic survey needs to know whether the seabed is stable. A gas study needs to know whether vents are shifting. A geological survey needs to know whether old maps are still reliable. A hazard assessment needs to know where deformation may threaten infrastructure. The link to oil and gas is never far away. Mud volcanoes are often seen as signs of hydrocarbon systems because methane, bitumen, and oil traces can emerge with the mud. In exploration terms, they can be clues. In environmental terms, they can be natural sources of hydrocarbons that must be separated from industrial pollution. In safety terms, they can mark pressurized pathways and unstable sediments. That means the same feature may interest several groups for different reasons. A geologist may see a window into basin dynamics. An energy company may see a hint of subsurface resources or a hazard near infrastructure. An environmental scientist may see methane emissions and altered habitats. A ship captain may see a place best given a little extra room. This overlap can make research access difficult. If a mud volcano field lies near oil infrastructure, it may also lie inside an area with industrial restrictions or safety rules. If it sits near a national boundary or a sensitive offshore zone, permission may be complicated. If it is shallow, navigation may be tricky. If it is deep, sampling may require expensive equipment. If it is actively venting, the risks increase. And if it is remote, everything becomes slower and more costly. Scientists may want to go there, but wanting is not a vessel, not a permit, not a weather window, and not a winch cable rated for whatever the Caspian has planned for Tuesday. Mud volcanoes also create problems for mapping. Seafloor mapping depends on sound, using sonar systems to measure depth and shape. Gas bubbles in the water can interfere with acoustic signals. Soft mud flows can have weak boundaries. Fresh deposits can change quickly. A mound may not have a simple form. Some features are low relief and broad. Others rise sharply. Some may be eroded by waves and currents, especially if they reach shallow water or become islands. NISA's 2026 piece notes that the tails of certain tadpole-shaped mud volcano islands are likely caused by currents eroding weak mud deposits and redepositing sediment on the sheltered side. That means even after an eruption, the work is not done. The sea continues editing the feature. Waves cut into it. Currents stretch sediment away. Loose mud settles. Gas pathways may close or reopen. A newly formed island may become a bank, then a shallow spot, then vanish from the surface. For a chart maker, this is annoying. For a geologist, it is useful. For a ship, it is a reason to proceed carefully. The Caspian does not only hide hazards below the surface. In some places it creates them, erases them, and creates them again. A study on environmental impact and sedimentary structures of mud volcanoes in the Caspian region describes the South Caspian Basin as a unique place to study mud volcanism and fluid flow in an active pierced basin, with over 400 active mud volcanoes onshore and offshore in the broader region. It also notes that submarine mud volcanoes can release waters and other components into the sea, that their gases are mainly methane with smaller amounts of other hydrocarbons and non-hydrocarbon gases, and that seafloor mud volcanoes can form islands and banks that alter topography and coastline. The phrase, active pierced basin, is one of those scientific phrases that sounds as though the Earth went to a rather intense tailor. But it is useful. It suggests a basin punctured by pathways, where material can rise through overlying sediment. A pierced basin is not sealed and still. It has routes upward. It has leakage. It has structures that connect deeper layers to the seabed. For scientists trying to understand the Caspian, this is both a clue and a complication. It means the seafloor can reveal the deep basin, but it also means the seafloor may not be stable, clean, or easy to interpret. There is also a chemical side to the breathing seabed. When methane enters sediment near the seafloor, microbes can consume some of it. In many marine environments, anaerobic oxidation of methane occurs below the sediment surface linked to sulfate reduction. This can create chemical gradients, carbonate formation, and distinct microbial zones. The exact processes vary by location, but the principle is that seepage creates chemistry, and chemistry creates habitat. If scientists want to measure methane emissions to the water or atmosphere, they need to know how much methane is produced, how much is consumed in sediments or water, how much reaches the surface and how much escapes. That is not easy. Methane can move in bubbles, dissolve in water, or be consumed before it ever reaches the air. The Caspian's closed nature, variable depth, and unusual salinity add more complexity. For sleep narration, this may sound like a long journey from mud to microbes, but that is how real science tends to behave. You start with a bubbling patch of seabed and end up discussing tectonics, climate, bacteria, petroleum, mapping, and whether your sampling bottle has leaked. The Earth rarely respects departmental boundaries. Mud volcanoes are geology, chemistry, biology, climate science, hazard science, and industrial safety all at once. They are multidisciplinary, which is a formal way of saying they cause meetings with too many people in them. The hazards are also not evenly distributed. Some mud volcanoes may be weakly active, some may be dormant, some may produce gentle seepage for long periods, others may erupt with little warning. Some are on land where scientists can access them more easily, which is why Geomar researchers noted that Caspian region mud volcanoes on land are more accessible than submarine ones. But the underwater features are important because they directly affect the sea. They can release methane into water, they can alter seabed topography, they can influence sediments near offshore infrastructure, they can form banks or islands, they can create areas where direct sampling requires extra care. There is a very ordinary reason scientists may avoid them too. Equipment is expensive. A research cruise may carry instruments worth hundreds of thousands, or even millions of euros. There are corers, sonar systems, methane sensors, remotely operated vehicles, cameras, sampling frames, and navigation equipment. Lowering them into an unstable gas-rich vent field is not something done casually. If a cable snags, if a frame sinks too deeply into soft mud, if gas expansion damages a sample, if a sensor is contaminated by oil, the loss is not just financial. It may cost the whole expedition valuable time, and research vessels like hotel minibars have a way of making every hour surprisingly expensive. This is why scientists often study mud volcanoes indirectly before approaching them. They may start with satellite imagery, seismic data, old eruption records, bathymetric maps, and reports from local agencies or previous expeditions. They may identify safe approach routes. They may use acoustic methods to detect gas plumes. They may collect water samples near, but not directly on top of, a vent. They may use land-based mud volcanoes as easier comparison sites. They may return later with better equipment or in cooperation with national scientists who know the local conditions. None of this is cowardice, it is good practice. Curiosity is useful. Curiosity with a risk assessment is better. There is a difference between danger and uncertainty, and the Caspian offers both. Some dangers are clear. Methane can ignite, eruptions can be violent, soft sediments can trap equipment, old installations can obstruct work. Uncertainty is quieter. It asks, is this vent active? Has the seabed shifted? Is this gas natural or linked to industrial activity? Are there buried structures? How old is this mud flow? Could a small eruption happen during sampling? Is this area legally accessible? Uncertainty can be managed. but it cannot be ignored. A scientist who ignores uncertainty is not being brave. They are simply making the paperwork more interesting for someone else. The breathing seafloor also changes how we think about avoidance. When scientists avoid certain mud volcano areas, they may not be avoiding the whole feature forever. They may be avoiding a specific vent during active release, a shallow bank after an eruption, an area near infrastructure, a place with unclear bathymetry, or a site where permissions are not in place. Another team may study the same general area later under safer conditions. Avoidance is often temporary, conditional, and method-based. It is not always a red cross on a map. Sometimes it is a note saying, "Not with this vessel, not in this weather, not with this equipment, and certainly not before lunch." There is something quietly humbling about these features. Mud volcanoes remind us that the seafloor is not only a floor, it is a boundary between the water above and the pressured world below. In the Caspian, that boundary is thin enough in places for gas, mud, salt water and hydrocarbons to move upward. The surface may be calm, but the basin beneath is still working. It is compacting, faulting, generating gas, releasing fluids and building small temporary landscapes out of mud. It has been doing this long before any platform stood there, and it will continue long after many platforms are gone. For scientists, the challenge is not only to avoid danger, it is to understand how these systems behave over time. Are emissions increasing or decreasing? Which vents are active? How much methane is released? How much is consumed before reaching the atmosphere? How do eruptions affect local ecosystems? How do mud flows interact with pipelines or old infrastructure? How often do islands form and vanish? Which areas are most likely to deform? Each answer requires data, and each data point requires someone to decide how close is close enough. So the mud volcanoes of the Caspian are not simply strange scenery. They are one of the reasons this inland sea remains difficult to study. They complicate maps, release methane, change sediments, mark hydrocarbon pathways, and sometimes produce sudden eruptions powerful enough to create temporary islands or fireballs. They are scientifically valuable because they reveal hidden processes, and scientifically inconvenient because they do not reveal them politely. And once we understand that the seafloor can breathe, bubble, and occasionally throw mud upward with enthusiasm, the next question becomes even more specific. What exactly is coming out of it? Mud is visible, islands can be photographed, fireballs make themselves rather hard to miss, but some of the most important Caspian hazards are invisible, rising quietly through water as gas, dissolving into sediments, feeding microbes and linking the deep basin to the air above. That brings us to methane, the quiet whisper beneath still water, and the reason some calm places are watched more carefully than they first appear. Mud is visible, islands can be photographed, fireballs make themselves rather hard to miss. But some of the most important Caspian hazards are invisible, rising quietly through water as gas, dissolving into sediments, feeding microbes, and linking the deep basin to the air above. That brings us to methane, the quiet signal beneath still water, and the reason some calm places are watched more carefully than they first appear. Methane is a simple gas, at least on paper. One carbon atom, 4 hydrogen atoms, tidy enough to make chemistry students feel briefly optimistic. It is the main component of natural gas, it burns easily, and it is produced in several ways. Some methane comes from deep heat and pressure acting on buried organic matter over long periods. Some comes from microbes breaking down organic material in low oxygen environments. In the Caspian region, both deep hydrocarbon systems and shallower biological processes can matter, which means that when methane appears, the first question is not only, how much is there? It is also, where did it come from? And that question is much harder to answer when the seafloor has faults, mud volcanoes, old oil fields, buried sediments, and natural seeps all sharing the same crowded address. The Caspian is especially interesting because its methane is not only an industrial topic, it is also a geological topic. Around Azerbaijan and the South Caspian Basin, Mud volcanoes and gas seeps occur where hydrocarbons have accumulated in sedimentary basins and where pressure pushes fluids and gases upward through weak pathways. NASA describes these mud volcanoes as features that eject cold slurries of mud, water, methane, and other gases rather than molten lava, and notes that Azerbaijan has at least 220 mud volcanoes, with some researchers putting the number closer to 350. The same NASA account also describes at least 140 underwater mud volcanoes in the South Caspian Sea along Azerbaijan's coast. This matters because methane does not need to wait politely for a drilling platform to release it. It can move naturally, it can seep through sediment, it can escape through mud volcano vents, it can rise in bubbles, it can dissolve into water, it can be consumed by microbes before it gets very far, or, under the right conditions, it can reach the surface and enter the atmosphere. The difficulty is that each pathway leaves a different kind of evidence. A bubble stream is obvious if your instruments are looking in the right place. Dissolved methane is less obvious. Microbial consumption is quieter still. Methane trapped in sediment or hydrate is another matter entirely. For scientists, the Caspian's methane is not one big leak with a label on it. It is a set of moving signals, some loud, some faint, some temporary, and some hidden under mud that does not care how expensive the equipment is. Geomar researchers have described Central Asian mud volcanoes as a significant source of atmospheric methane, and noted that gas venting from mud volcanoes may contain up to 90% methane. They also point out two practical concerns. Methane is climate relevant because it's a strong greenhouse gas and it is easily flammable, which makes it a natural hazard in active mud volcano regions. That is why a calm-looking patch of water above a vent field is not automatically treated as safe or simple. Nothing about the surface necessarily tells you how much gas is moving below it. Water is very good at looking innocent. It can cover a seep, a pipe, a soft mud deposit, or a gas-charged sediment pocket with the same plain blue or grey expression. The flammability is the part that tends to catch attention, because fire is easier to picture than chemistry. When methane rises and ignites, the result can be dramatic. Guillemard described a sampled Azerbaijani mud volcano that had erupted and gone ablaze shortly before their fieldwork, and DLR reported that the Otman Bostak mud volcano erupted explosively on October 11th, 2025, producing a sudden natural methane release and a tall flame above the crater. DLR's team then carried out ground measurements and drone flights shortly after the eruption, once permits were obtained. That is a helpful example of how scientists work around risk. They do not simply rush into a fresh eruption site because it looks exciting. They wait for permissions, plan the measurements, choose the right method, and use tools that keep people safer. In the DLR project, researchers used a fixed-wing drone equipped with high-precision methane and wind sensors, flying patterns around mud volcanoes to estimate methane fluxes from upwind and downwind measurements. That approach allows researchers to measure emissions without standing in the most dangerous place, with a notebook and an expression of professional regret. Drones are useful because methane measurement is not as easy as sniffing the air and nodding wisely. To understand an emission, researchers need concentration and wind data. A high methane reading means less if you do not know how air is moving. A weak reading might still matter if the gas is spread over a large area. A vent that releases gas steadily all year may matter differently from one that erupts violently for a short period. DLR notes that Azerbaijani mud volcanoes vary greatly in activity. Some emit gas continuously, while others remain dormant for long periods before erupting explosively for short durations. This makes measurement difficult because the source is not always behaving the same way. It is a little like trying to measure how talkative a person is by checking on them once during a nap. This variability is one of the reasons certain parts of the Caspian are avoided or only approached under controlled conditions. A vent field that appears quiet may not be dead. A mud volcano that has not erupted recently may still release gas. A submarine feature may be active without producing anything visible above the water. A research vessel working over such a place needs to think about gas bubbles, soft seabed, possible ignition sources, and the simple problem of whether the instruments will collect a useful sample or just return with mud in all the wrong places. At sea, a surprise does not have to be large to ruin the day. Sometimes a little lost equipment is enough. Methane also matters because it can change what happens inside the sediment. Where methane moves upward through mud, microbes may use it as an energy source. In many low-oxygen sediments, microbial communities can consume methane before it escapes. This can reduce the amount reaching the water or air, but it also changes the chemistry around the seep. Sulfate, sulfide, carbonate, dissolved metals, and oxygen conditions can all be affected. A sediment core from a methane seep is therefore not just mud. It is a small chemical column with layers that may show where methane is being produced, consumed, or transported. Bring that core to the surface, and the pressure changes. Gas can expand, fluids can move, the sample may shift. The scientist has to work carefully because the sample is not a dead object. It is a small, disturbed piece of an active system. Then there is the issue of bubbles. Methane can travel as dissolved gas, but it can also rise as bubbles through the sediment and water column. Bubbles are both helpful and annoying. They are helpful because sonar can sometimes detect them as acoustic plumes, letting scientists locate active seepage. They are annoying because bubbles do not behave like a neat pipe. They rise, dissolve, merge, break apart, and may be affected by depth, temperature, pressure, salinity, and currents. A bubble released in shallow water may have a better chance of reaching the atmosphere than a bubble released in deeper water because it has less distance to travel and less time to dissolve or be consumed. A deep bubble may lose much of its methane into the water before it reaches the surface. The Caspian has shallow northern waters and deep southern waters, so the same gas release can have different outcomes depending on where it happens. The deep water question brings us close to gas hydrates. Gas hydrates are ice-like solids in which gas molecules, often methane, are trapped inside cages of water molecules under suitable pressure and temperature conditions. Submarine mud volcanoes around the world are often associated with gas hydrates, and a major review noted that gas hydrates have been observed in association with mud volcanoes in the Caspian Sea, among other regions. The same review describes submarine mud volcanoes as sources of methane flux from the lithosphere into the hydrosphere and atmosphere, and also notes that such activity can affect drilling operations, ring installations, and pipeline routing. Gas hydrate sounds rather neat, like something you might find in a freezer if your freezer had poor boundaries and an alarming relationship with geology. But hydrate-bearing sediments can be difficult to sample. If pressure and temperature change as material is lifted from the seabed, hydrate can dissociate, releasing gas and water. That can disturb the sample and alter measurements. In some settings, hydrate-coated bubbles may carry methane upward more efficiently through the water column. A well-known study outside the Caspian, at a deep-sea submarine mud volcano, described methane discharge into the upper water column by gas hydrate-coated bubbles, which shows why scientists pay attention to the physical form methane takes, not only the amount released. For the Caspian, this means methane is not only a how much problem, it is a what form, what depth, what pathway, and what fate problem. Does it stay trapped below the seabed? Does it move through faults? Does it dissolve into bottom water? Does it feed microbes? Does it reach the surface? Does it enter the air? Does it emerge naturally? Or is it linked to disturbed sediments, old wells, or industrial infrastructure? These questions sound calm, but they are not small. They affect climate accounting, hazard assessment, oil field safety, ecosystem research, and how governments and companies manage offshore activity. The climate part is especially important because methane is a powerful greenhouse gas. Older summaries often compare it with carbon dioxide using one time scale, while newer climate assessments use several time horizons, so the exact comparison depends on the method. The practical point remains steady. Methane matters for warming, especially over shorter time periods. That is why geological methane sources such as mud volcanoes are being measured more carefully. DLR's 2025 project was carried out as part of the International Methane Emissions Observatory, an initiative of the United Nations Environment Programme, with the aim of better quantifying poorly understood geological methane sources and comparing them with mainly human-caused sources. This distinction between natural and human-caused methane is not just academic. If satellites or aircraft detect methane above the Caspian region, researchers need to know whether it came from a mud volcano, an oil and gas facility, a pipeline, a wetland, a landfill, livestock, or some combination. Around an active hydrocarbon province, that separation is hard. A natural seep may sit near industrial infrastructure. A mud volcano may emit methane naturally while nearby equipment emits methane accidentally. A satellite may detect a plume without immediately telling you which source caused it. Field measurements, wind modelling, chemistry, isotopes and local knowledge are all needed. Without them, it is easy to point at the wrong suspect, which is awkward in science and even more awkward in environmental regulation. This is another reason some places are avoided until a proper survey can be arranged. Measuring methane near oil fields, ports, restricted zones, or mud volcanoes is not just a technical job. It can be sensitive. Data may touch questions of emissions reporting, industrial responsibility, natural hazard, or national resources. A research team has to work within permissions and with reliable methods, because a bad measurement can cause confusion. In a place like the Caspian, where natural geological methane and industrial methane may exist side by side, precision matters. You do not want to confuse a mud volcano with a leaking facility, or a leaking facility with a mud volcano, any more than you want to blame the dog for a noise made by the fridge. The water itself also complicates the matter. Methane released into the Caspian does not automatically go straight into the atmosphere. Some dissolves in water, some is oxidized by microbes, some may be transported by currents. Some may remain in deeper layers if mixing is limited. This is why oceanographers and geochemists need profiles from different depths, not just surface readings. They may lower sensors through the water column to measure methane, oxygen, temperature, salinity, and other variables. They may take water bottles at specific depths. They may collect sediment cores. They may use sonar to find bubble plumes. Each method sees part of the system. None sees everything alone. In shallow water, methane may reach the atmosphere more easily, but shallow water brings its own problems. The vessel may have trouble operating. The seabed may be too soft. The area may be full of old structures, pipelines, or restricted zones. In deeper water, the ship may operate more easily, but the methane pathway may be harder to interpret because gas can dissolve or be consumed before reaching the surface. Deep sampling needs heavier equipment, longer cables, more time, and more stable weather. So the Caspian gives researchers a choice between awkward, shallow work and expensive deep work, which is a little like being offered either cold tea or no tea at all. Methane also connects to oxygen, and that becomes important as we move toward the deeper Caspian. When microbes consume methane, they can use oxidants such as oxygen or sulfate depending on the environment. In water, methane oxidation can consume oxygen. In sediments, methane-related microbial reactions can shape low oxygen and sulfide-rich zones. This is not automatically catastrophic, but it matters in enclosed or stratified systems where oxygen supply is limited. If bottom waters do not mix well, oxygen can become depleted. If organic matter, hydrocarbons, or reduced gases increase microbial demand, the situation can become more sensitive. The Caspian's deeper basins are not just dark because sunlight fails to reach them. They are chemically different places, with slower exchange and more delicate balances. This is where the word quiet becomes useful in a practical sense. A methane seep can be quiet. Not silent perhaps, but quiet to ordinary human senses. No flame, no explosion, no island, no smell at the surface. Just a slow movement of gas through sediment and water. Scientists may avoid such a place not because it looks frightening, but because it does not show enough. The absence of drama can be misleading. A calm surface can hide active chemistry. A flat seabed can hide gas. A weak seep can still matter over years. A dormant mud volcano can become active. A deep methane signal can affect oxygen and microbial life without ever making a visible bubble ring on the surface. The instruments used to study this are often delicate. Methane sensors need calibration. Water samples must be sealed correctly to prevent gas loss. Sediment cores need careful handling so gases do not escape before analysis. Isotope samples must avoid contamination. Drone and aircraft measurements need accurate wind data. Satellite detections need validation. If a scientist says, we should not go directly into that area yet, they may not be saying, it is too scary. They may be saying, if we go now with the wrong tools, we will not learn what we think we are learning. That is less dramatic, but it is much more common. Methane also has a way of making boundaries blurry. It belongs to geology because it forms and migrates underground. It belongs to chemistry because it reacts and dissolves. It belongs to biology because microbes consume and produce it. It belongs to climate science because it can warm the atmosphere. It belongs to engineering because it can affect drilling, pipelines and platforms. It belongs to law and policy because emissions have to be reported, managed, and sometimes argued about in rooms with very bright lights and not enough biscuits. The Caspian brings all of those fields together in one complicated basin. And because the sea has no easy natural outlet, methane-related chemistry can be part of local and regional water conditions. The gas itself may escape or be consumed, but the reactions around it leave traces. Carbonates may form, sediment chemistry may change, microbial communities may cluster around seepage, hydrocarbon signals may mix with industrial pollution. In a closed inland sea, those local signatures can matter more than they would in a better flushed environment. The Caspian does not always dilute stories quickly. It stores them, layers them, and sometimes lets them rise again. The most careful scientists are not trying to make the Caspian sound more dangerous than it is. They are trying to make the danger specific. Methane is not a sea monster. It is not waiting below the boat with a little villain hat. It is natural gas moving through a complex basin, sometimes joined by industrial emissions, sometimes trapped, sometimes released, sometimes burned, sometimes measured, and often misunderstood. The danger lies in treating it too simply. If you imagine methane only as an explosion risk, you miss its climate role. If you imagine it only as a climate gas, you miss its geological and microbial pathways. If you imagine it only as natural, you may ignore industrial leaks. If you imagine it only as industrial, you may misread the mud volcanoes. The Caspian keeps all these possibilities close together, which is generous scientifically and inconvenient practically. So the methane whisper beneath quiet water is one of the clearest reasons scientists still choose caution. A vessel may stay away from a known vent until conditions are safe. A team may use a drone rather than walk a crater. A survey may map bubbles with sonar before dropping equipment. A sampling plan may avoid active infrastructure while still measuring nearby natural seepage. A satellite image may guide the first questions before anyone leaves port. The work continues, but it continues carefully. In the Caspian, caution is not the opposite of exploration. It is the method that makes exploration possible. And as methane rises, dissolves, burns, or disappears into microbial work, it leads us deeper into the sea's hidden chemistry. Because gas is only part of the story. Below the surface, especially in the deeper southern basin, water can become layered, slow to mix, and low in oxygen. The same enclosed geography that holds salt, sediments and hydrocarbon signals also shapes the breathing of the water itself. To understand why some places are hard to study, we have to sink below the vents and slicks into the darker layers, where the concern is not fire or bubbling mud, but the heavy depths where oxygen fades. Below the vents and slicks, below the places where bubbles rise and mud moves, the Caspian becomes a different kind of problem. Not louder, not more dramatic, just heavier, darker, slower, and much harder to read from the surface. The southern basin drops to more than 1,000 meters, and once water gets down into those depths, it does not behave like the bright surface water where wind can stir it and sunlight can warm it. It settles into layers. It moves slowly. It holds chemical signals for long periods. And in some of those deep layers, oxygen can become scarce enough that scientists have to treat the water not as ordinary deep water, but as a sensitive, changing environment that may be difficult to sample and difficult to interpret. The Caspian's maximum depth is about 1,025 meters in the southern basin, while its shallow northern basin and deeper middle and southern basins behave very differently, which is why researchers cannot treat the whole sea as one simple body of water. Oxygen sounds simple because we live in it all day without thinking about it, unless we're climbing stairs after promising ourselves we're definitely getting fitter this year. In water, though, oxygen is not guaranteed. It has to enter, mix, move, and remain available. At the surface, oxygen can enter from the atmosphere and from photosynthesis by tiny algae and other organisms. Wind can stir the upper layers. Cooling can make surface water denser, helping it sink. But for oxygen to reach deep water, the water column has to allow some kind of renewal. Dense oxygen-rich water has to move downward, or deep water has to be replaced by water from elsewhere. In the open ocean, this is part of global circulation. In the Caspian, there is no connection to the open ocean, so renewal depends on local and regional processes inside the basin itself. That is where the difficulty begins. The deep Caspian is not simply refilled with fresh oxygen every time the wind blows. Wind can stir the surface, but it may not reach the deepest layers. Sunlight feeds life near the top, but not in the dark basin below. Organic material produced near the surface can sink downward, and as it decays, microbes consume oxygen. Methane and other reduced compounds can also contribute to chemical oxygen demand. If oxygen is used faster than it is replaced, the deeper water becomes hypoxic, meaning low in oxygen. If it becomes even more depleted, it can approach anoxic conditions, where oxygen is absent or nearly absent. For animals living on or near the seafloor, this is not a small inconvenience. It is the difference between a livable habitat and a place where only certain microbes and chemical processes can manage. This is one reason deep parts of the Caspian can be scientifically awkward. A surface sample may tell you very little about what is happening at depth. The top layer might look normal while the bottom layer is oxygen poor. A boat can cross over the deepest basin without seeing any sign of the chemistry below. There may be no colour change, no smell, no warning ripple. Just a water column that changes with depth, metre by metre, until the lower layers become a different chemical world. To understand it, researchers need vertical profiles. They need instruments lowered through the water, stopping at different depths to measure temperature, salinity, density, oxygen, nutrients, methane, pH, and sometimes many other variables. It is not enough to scoop water from the side and say, well, that seems wet. The Caspian's deep water exchange has been studied using traces such as tritium, helium, chlorofluorocarbons, oxygen, temperature and salinity. One major study estimated deep water exchange rates of about 7% per year in the southern and central basins, and estimated oxygen depletion in deep water at about 0.35 milligrams per litre per year. The same study noted that the processes responsible for deep water exchange were not identified conclusively, and that seasonal cooling alone may not be enough to trigger large-scale convection in the southern and central basins. That last point is important. If seasonal cooling were enough, the story would be simpler. Winter arrives, surface water cools, gets denser, sinks, carries oxygen down, and the deep basin gets a nice fresh delivery, like milk at the door in an old film. But the Caspian is not always that cooperative. Its density structure depends on temperature, salinity, suspended sediment, river inputs, and circulation between basins. Water from the central basin can move southward and mix down to certain depths, and rare or strong events may matter. But the deeper system is not refreshed with the easy regularity of a kitchen tap. It is more like a house where the air in the attic only changes when several doors, windows, and weather conditions happen to agree. Layering or stratification is the key. Water becomes stratified when layers of different density resist mixing. Warm water usually sits above colder water. Fresher water can sit above saltier water. In the Caspian, river inflow, evaporation, temperature, basin shape, and seasonal heating all help create layers. During warm months, the surface layer heats up and becomes lighter, making it harder for oxygen to move downward. During colder months, the surface can become denser, and mixing can deepen, but not always enough to reach the bottom. The result is that deep water can remain isolated for long enough that oxygen declines. A recent UNEP working paper on Caspian Sea fluctuations says that warming trends and human activities have led to water column stratification, oxygen depletion, and hypoxia, especially below 400 metres. Below 400 metres is not a place most people imagine when they picture the Caspian. We tend to think of ports, beaches, fishing boats, oil platforms, and brown-green water near shore. But the southern basin is deep enough to contain a large dark volume where the normal surface story does not apply. The lower water is colder, more stable, and slower to mix. Instruments sent there need long cables or advanced profiling systems. The ship must hold position. Weather must cooperate. The winch must work. The sensors must survive pressure. Samples must be brought back without losing gases or changing chemistry too much. And if researchers are working near areas with mud volcanoes, methane seepage, or old oil infrastructure, the chemical story gets even more complicated. Hypoxia also affects biology. Many fish and larger bottom-dwelling animals cannot live in very low oxygen. Smaller organisms may tolerate some stress, but only up to a point. Microbes take over where oxygen is low, driving chemical reactions that can release or transform nutrients, metals, and gases. Phosphorus, nitrogen compounds, silica, carbon dioxide, methane, hydrogen sulfide, and other substances can behave differently when oxygen fades. One 2022 study of the southern Caspian reported that hypoxia continues to intensify in the deep-water basin of the South Caspian Sea. It found near-zero dissolved oxygen and accumulation of phosphate, silicate, and total dissolved inorganic carbon in near-bottom layers, indicating that winter mixing had not reached the near-bottom layers during that survey. This is where the deep Caspian becomes less like a simple body of water and more like a stack of separate rooms. The surface room has wind, light, waves, plankton, and direct contact with the atmosphere. The middle room has changing temperature, salinity, and currents. The bottom room may be quiet, low in oxygen, and chemically active in ways that are easy to miss without the right instruments. If the doors between those rooms do not open often, oxygen does not move down efficiently. Material from above still sinks, microbes still work, and oxygen keeps being consumed. In that situation, the deep basin can become more and more oxygen poor, even while the surface still looks completely ordinary. For scientists, low oxygen is not usually a reason to panic, but it is a reason to plan. Instruments measuring oxygen must be calibrated carefully. Water bottles must close at the correct depth. The crew must avoid contamination from the ship. Sediment caused from low oxygen environments must be handled quickly if the chemistry is to be preserved. Some compounds change when exposed to air. Hydrogen sulfide, if present, can be toxic, and can also react rapidly. Reduced sediments can change colour and chemistry once oxygen touches them. So a deep sample is not just a souvenir from the bottom, it is a fragile record of conditions that may change the moment it is disturbed. There is also a safety issue, though not always the obvious kind. Low oxygen at depth does not mean the air above the ship is unsafe. The crew is not going to lean over the rail and suddenly run out of breath because the bottom water had a difficult afternoon. The risk is more technical and chemical. Samples can contain gases. Sediments can release unpleasant or hazardous compounds. Equipment can come up coated in anoxic mud. If methane or sulfide-rich material is involved, the team must use proper handling procedures. It is not a horror scene. It is a laboratory scene, which is often more controlled but sometimes smells worse. The deep water problem also makes certain areas scientifically frustrating. The deepest and most chemically interesting places may be costly to reach. A research cruise may only have enough time for a limited number of deep stations. Weather can shorten the schedule. Permits may limit where the vessel can go. Industrial zones may require avoidance. If a deep station is near a sensitive border, an oil field, or a known seep area, the logistics grow more complicated. Scientists may know exactly where they want to sample, but knowing the ideal location is not the same as being able to put a ship there. The sea, the law, the budget, and the calendar all get a vote. And then there is the issue of long-term monitoring. Oxygen depletion is not fully understood from one cruise. A single set of measurements can tell you what was happening during that season, in those weather conditions, at those stations. But deep basins change over years and decades. The Caspian's water level changes, climate warms, river discharge varies, nutrient inputs change, industrial pressure rises or falls, invasive species alter food webs, organic matter production shifts. Deep water may renew in rare events that a single expedition misses completely. If you only visit between such events, you may think the system is more stagnant than it is. If you happen to visit soon after renewal, you may think it is healthier than it usually is. The Caspian can be very good at making a brief survey feel confident for no reason. This is one reason scientists often combine field measurements with models and historical data. They use old records of temperature, salinity, and oxygen. They use current meters. They use satellite observations for the surface. They use bathymetric maps to understand basin shape. They use chemical tracers to estimate water age. They use numerical models to test how circulation might carry oxygen downward. But the Caspian remains underobserved in some areas. A frontier study on southern Caspian currents notes that many recent studies have relied heavily on models and recorded temperature and salinity data, while accurate field measurement has received less attention because of equipment availability and high field operation costs. The same paper points to gaps in field data on flow patterns, seawater properties, and physical processes in the southern shelf and basin. That line, high costs of field operations, may sound plain, but it explains a lot. Scientific avoidance is sometimes not about danger at all. It is about limited resources. A deepwater oxygen survey needs a suitable vessel, trained crew, CTD systems, oxygen sensors, sampling bottles, laboratory support, spare parts, fuel, permissions, data processing, and enough time at sea to get a useful picture. If the same area is also politically sensitive, industrially active, or hard to reach in bad weather, the cost rises. Researchers may decide to sample nearby, use older data, or wait for a larger coordinated expedition. From the outside, that can look like avoidance. From the inside, it is simply the mathematics of doing difficult science without unlimited money, which, sadly, remains a common condition. Low oxygen also links back to pollution. Organic pollution and nutrient loading can increase biological production near the surface. When that organic material sinks and decomposes, it can consume oxygen at depth. Oil contamination and hydrocarbon inputs can also stimulate microbial processes that use oxygen or other chemical oxidants. In a closed basin, these pressures can combine. The Caspian receives inputs from large rivers and coastal cities, and parts of it are affected by oil and gas activity, shipping, and industry. Not every low oxygen problem is caused by pollution, and it would be careless to say so. Stratification and natural basin shape are major factors, but human activity can make oxygen stress worse, especially in areas with poor water exchange. This is why the deep basin matters even if most people never see it. Oxygen loss can change nutrient cycling, and nutrient cycling can affect surface productivity. Low oxygen bottom waters can influence what organisms live on the seabed. Chemical changes in sediments can release phosphorus or alter nitrogen compounds. If methane is present, oxygen depletion can change how much is consumed before reaching higher layers. If hydrogen sulfide builds up in sediments or bottom waters, it creates another layer of concern for animals and sampling work. The deep Caspian is not separate from the rest of the sea. It is connected slowly, chemically, and sometimes surprisingly. A useful way to picture this is to think of the deep basin as a storage room beneath a busy house. The upstairs rooms are full of movement. People open doors, make food, argue about where the keys are, and generally behave like a surface ecosystem. Downstairs in the storage room, things are slower. Boxes accumulate. The air may become stale if no one opens the door. If something leaks, it may sit there for a long time before anyone notices. The problem is not that the storage room is evil. It is that it is poorly ventilated, difficult to inspect, and full of things people forgot they put there. The deep Caspian is more complex than that, of course, but the general warning is similar. What is out of sight can still shape the whole building. For research vessels, the heavy depths also pose physical challenges. Lowering instruments hundreds of meters takes time. A CTD rosette may descend slowly, measuring continuously, then pause at selected depths to close sampling bottles. In rough water, cables can sway. Currents can push the package. The ship's position matters. If the bottom topography is steep or uneven, the crew must avoid hitting the seabed. In areas with possible gas release or soft sediment, bottom sampling must be planned carefully. If a corer penetrates low oxygen mud, the sample may need immediate processing. If it returns with gas expansion, the team has to handle it safely. Deep work is slow by nature. It is not the place for impatience, which is unfortunate because ships are expensive and everyone secretly wants the schedule to move faster. There is also the risk of misreading the data. Oxygen sensors can drift. Samples can be contaminated by air bubbles. Depth sensors must be accurate. Salinity readings in the Caspian require attention because its brackish chemistry differs from standard ocean water. If researchers use ocean methods without adjustment, they may introduce errors. Deep oxygen gradients can be steep, so a small depth mismatch can matter. A value measured at 350 meters may tell a different story from one at 450 meters. When hypoxia is expected below a certain depth, the precise shape of the profile becomes important. This is the kind of work where a small mistake can quietly become a large wrong conclusion, which is why scientists are annoyingly careful and often correct to be so. Climate change adds more pressure. Warmer surface water tends to strengthen stratification because warm water is lighter. Stronger stratification can reduce vertical mixing. If evaporation increases and river inflow changes, salinity and density structure can shift. Falling water levels can alter shelf areas, wetlands, and circulation patterns. Changes in wind can affect mixing and currents. None of these processes act alone. The Caspian is responding to climate, river management, local industry, and internal circulation at the same time. When researchers see oxygen depletion, they must ask which factors are responsible and how they interact. The answer may vary between the northern shallows, the central basin, and the deep south. This makes deep water oxygen one of the less visible but more important reasons for scientific caution. It is not as photogenic as a mud volcano island, and it will not sell many posters. You cannot easily show near zero dissolved oxygen in a dramatic thumbnail unless you put a worried fish next to a gauge, which is probably unfair to the fish. But oxygen tells researchers whether deep habitats are under stress. It tells them whether water renewal is happening. It tells them how the basin is changing. It affects chemistry, biology, methane cycling, and the long-term health of the sea. If scientists avoid or delay work in certain deep areas, it is often because the work must be done carefully enough to be meaningful. The strange part is that the deepest water can look calm in the data and still be troubling. A stable layer is stable, which sounds good, but too much stability can mean poor ventilation. A quiet bottom can preserve sediments, but it can also preserve contamination. Slow circulation can make changes easier to track, but it can also allow oxygen depletion to intensify. The Caspian keeps reminding us that calm is not always the same as healthy. Sometimes calm means undisturbed. Sometimes it means stagnant. Sometimes it means nobody has measured it recently enough to know. So the heavy depths where oxygen fades are avoided not because they are forbidden by nature, but because they demand time, equipment, permission, and precision. They are hard to sample, easy to misunderstand, and important enough that bad data may be worse than no data. They sit below the more visible stories of oil, mud volcanoes, and methane, quietly shaping the chemistry of the sea from underneath. A research team entering these waters has to think vertically, not just horizontally. The map may show a point on the surface, but the real question lies in the column below it, from wind-mixed topwater to darker layers where oxygen thins and chemistry changes. And yet, even if a team has the right ship, the right sensors, the right weather, and a perfect plan for lowering instruments into the deep, there is another kind of boundary waiting above the water. It is not made of mud or methane. It does not show up as a low oxygen layer on a profile. It appears on charts, legal documents, permits, and patrol schedules. Because the Caspian is not only a body of water, it is also divided between countries, watched by authorities, crossed by energy routes, and shaped by agreements that decide who may study what, where, and when. Even if a team has the right ship, the right sensors, the right weather, and a perfect plan for lowering instruments into the deep, there is another kind of boundary waiting above the water. It is not made of mud or methane. It does not show up as a low oxygen layer on a profile. It appears on charts, legal documents, permits, and patrol schedules. Because the Caspian is not only a body of water, it is also divided between countries, watched by authorities, crossed by energy routes, and shaped by agreements that decide who may study what, where, and when. This is one of the least cinematic reasons scientists avoid certain parts of the Caspian Sea, but it is also one of the most important. The Caspian is bordered by 5 countries: Russia, Kazakhstan, Turkmenistan, Iran, and Azerbaijan. None of them is just casually standing beside it, waving at the waves. Each has coastlines, ports, resource interests, fishing interests, security concerns, environmental responsibilities, and legal claims. So when a research vessel moves across the Caspian, it is not only moving through water, it is moving through a carefully managed political space. A few kilometres in the wrong direction can matter. A sampling station that looks harmless on a map may fall inside a territorial zone, a fishery zone, an oil block, a military area, a pipeline corridor, or a place where research needs written approval before anyone even opens the box of sample bottles. This is one of those situations where the surface lies by being too smooth. A border on land may have fences, signs, checkpoints, roads, and tired-looking buildings where people inspect documents. At sea, there may be none of that. There may only be open water and a GPS screen. But the border still exists. It is invisible to the eyes and very visible to the people responsible for enforcing it. For scientists, that means maps are not only geographical tools, they are legal tools. Coordinates are not just numbers, they are permission points. A station plan is not only a scientific design, It's also a document that may have to pass through ministries, agencies, navies, port authorities, environmental regulators, and sometimes energy companies, which is enough paperwork to make even a very patient oceanographer stare quietly into a mug of tea. The legal situation of the Caspian became especially complicated after the Soviet Union dissolved. Before 1991, the main coastal powers were the Soviet Union and Iran. After the Soviet collapse, Azerbaijan, Kazakhstan, and Turkmenistan became independent Caspian states, and suddenly the basin was shared by 5 countries rather than 2. That changed the entire legal puzzle. Oil and gas fields, fishing areas, navigation routes, military rules, and environmental duties all had to be renegotiated. Legal scholars have noted that the Caspian status became one of the major regional disputes after 1991, partly because the sea holds large biological and mineral resources, and partly because it does not fit neatly into ordinary categories of international law. It is enclosed like a lake, but large and salty like a sea. That sounds like a technicality, until money, pipelines, fish, security and research vessels become involved. Then the technicality puts on a suit and enters the room. For many years there was no single settled answer that satisfied all 5 states. The countries negotiated, argued, signed bilateral agreements in some places, and left other issues unresolved. Then, in August 2018, the 5 Caspian states signed the Convention on the legal status of the Caspian Sea in Aktau, Kazakhstan. The convention created a framework for dividing the water area into internal waters, territorial waters, fishery zones, and common maritime space. It gives each coastal state territorial waters up to 15 nautical miles from its baselines, followed by a 10 nautical mile fishery zone, and it sets rules for navigation, resources, and other uses of the sea. That may sound tidy. 15 miles here, 10 miles there, common space beyond, and everyone goes home for dinner. But the Caspian rarely allows things to remain that simple. The seabed and subsoil, where oil, gas, pipelines, and some scientific targets are found, are another matter. The 2018 framework leaves seabed delimitation to agreements between neighbouring and opposite states. In other words, the water surface has one set of zones, while the bottom beneath it may involve separate arrangements. For a scientist trying to study deep sediments, methane seepage, benthic habitats, or pollution near an offshore field, the bottom matters very much. You do not sample the water only as a legal idea. You lower equipment into a real place that may belong to one jurisdiction, lie near another, or sit close to resources that have been debated for decades. There is also the matter of whether the 2018 Convention has fully entered into force. Available 2025 legal summaries still noted that it had not yet entered into force because Iran had not ratified it, even though the 5 states signed it in 2018. That does not mean there are no rules. National laws, earlier agreements, bilateral arrangements, sectoral practice, environmental conventions, port regulations and security rules all still shape behaviour. But it does mean researchers cannot treat the convention as if it magically removed every complication. The Caspian became more organised after 2018, but not magically simple. For marine scientific research, permission is central. The convention text sets out that scientific research in territorial waters and research connected to biological resources, seabed or subsoil exploration, or their use, requires written permission from the relevant coastal state. It also gives the state that permitted research the right to require certain conditions, and research can be suspended in defined circumstances, including security concerns. That matters enormously for scientists. A marine biologist may want to study sturgeon habitat. A geochemist may want sediment cores near a seep. A climate team may want methane measurements. A geologist may want seismic profiles across a mud volcano field. Each of those activities can become legally different depending on where it happens and what it touches. This is why scientists may avoid certain areas, not because the water is physically dangerous, but because entering without permission would be illegal, unwise, or likely to end the project before it begins. A research vessel cannot behave like a curious duck. It cannot drift into a zone, dip its beak in, and leave. It carries flags, crew, equipment, data, and institutional responsibility. If it enters restricted waters without approval, the problem is not just embarrassing. It can become a diplomatic issue. It can damage relationships with local agencies. It can prevent future research. It can lead to inspections, delays, fines, or orders to leave. Good scientists plan for this. They do not simply hope nobody notices the boat. The Caspian also has security rules that affect access. The 2018 Convention reserves rights over the sea to the 5 coastal states and excludes military forces from non-Caspian countries. Analyses of the Convention note that it forbids military assets in the region from non-Caspian countries, and the agreement is often discussed not only as a resource document, but as a regional security document. This security background matters for research because scientific equipment can look suspicious if people do not know what it is. Sonar can map the seabed. Autonomous vehicles can travel underwater. Seismic systems can reveal subsurface structures. Drones can fly survey lines. These tools are normal in science, but they are also exactly the sort of tools that authorities may want explained very clearly, preferably before they appear near a sensitive port or energy installation. There is a slightly absurd side to this. A scientist may be trying to measure oxygen, methane, or plankton, while a security official sees a vessel carrying acoustic devices, GPS systems, drones, satellite communications, and people who keep saying things like sub-bottom profiler. From the scientist's point of view, the mission is environmental. From the authorities' point of view, it may need checking. Both reactions are understandable. The sea is shared, energy-rich, and strategically important. A research ship may be innocent, but innocence still needs paperwork. This is one of the quiet realities of modern field science. The best data sometimes begins with a form, not a discovery. Energy routes add another layer. The Caspian is crossed by pipelines, shipping lanes, service routes, offshore installations, and areas linked to oil and gas production. Some places are active industrial zones, others contain older infrastructure. Some seabed corridors may be protected for safety. If a research team wants to tow equipment across the bottom, lower a heavy corer, or anchor a vessel, they need to know what lies beneath. Hitting a pipeline, snagging a cable, or interfering with offshore operations is not a charming scientific mishap. It is an expensive and dangerous mistake. For this reason, researchers may avoid certain industrial waters unless they have detailed maps, permissions, and coordination with operators. This is one of the reasons Caspian research can feel like a slow chess game. The scientific question might be simple. Measure methane near a seep, sample sediments near an old oil area, map oxygen in deep water, monitor fish habitat, survey a coastline retreating as the sea level falls. But the route to that question passes through legal and practical filters. Which country's sector is it in? Is it near a territorial sea boundary? Is it inside a fishery zone? Is it close to a disputed or sensitive seabed area? Is there active oil and gas work nearby? Is it near a military site? Does the team need an environmental permit, a navigation permit, a sampling permit, a drone permit, an export permit for samples, or a local partner? The answer is often yes, and sometimes several yeses at once. Environmental law is another piece of this puzzle. The Tehran Convention, formerly the Framework Convention for the Protection of the Marine Environment of the Caspian Sea, was signed by the 5 Caspian states in 2003 and entered into force in 2006 after ratification by all 5 governments. It was developed under UNEP and remains the main regional environmental treaty for the Caspian, with protocols covering oil pollution response, land-based pollution, biodiversity, and environmental impact assessment. This means environmental research is not outside the political system. It is part of a regional framework where the states have agreed that pollution, biodiversity monitoring and environmental assessment are shared concerns. That sounds helpful, and it is. Cooperation makes research easier. Shared environmental rules can support data exchange and joint monitoring. But cooperation also has procedures. Data may need to be reported through official channels. Sampling may require coordination. Projects may need national approval. If research involves transboundary impacts, endangered species, oil pollution, or sensitive habitats, it may involve even more agencies. A scientist cannot simply say, "But it is for the environment," and expect every gate to open. The environment is exactly why some gates exist. Fishing zones matter too. The Caspian is famous for sturgeon, and its fisheries have long been politically and economically important. Each state has an exclusive 10 nautical mile fishery zone adjacent to its territorial waters under the 2018 framework. Research connected to aquatic biological resources can therefore be sensitive. Fish surveys, egg sampling, tagging, seabed habitat mapping, or work near spawning and feeding grounds may require special approval. This is not only about ownership, it is also about conservation, illegal fishing, commercial value, and national responsibility. A net, a trawl, or even a scientific sampling device can be treated very differently depending on where it is used and what species it may affect. This helps explain why some biological research is easier from shore, from local vessels, or through partnerships with national institutes. Local scientists know the rules, seasons, ports, and agencies. They may know which areas are sensitive because of fish migration, seal breeding, protected zones, or enforcement activity. International scientists often need that local cooperation not only to be polite, but to do the work legally and safely. Field science in the Caspian is rarely a lone heroic expedition. It is usually a coordinated effort, involving institutions, authorities, crews, and sometimes people whose main task is making sure everyone signs the correct document before the boat leaves. There are also areas where boundaries remain politically delicate. Some northern and western seabed divisions have been handled through agreements between Russia, Kazakhstan, and Azerbaijan, and other arrangements involve Turkmenistan and Kazakhstan. But the wider issue of seabed delimitation has not always been equally settled everywhere, especially where Iran's position has differed from the modified median line approach used by some other states. Legal analyses have noted that seabed delimitation has remained one of the most disputed issues in the Caspian, and that several bilateral and trilateral agreements develop before or alongside the wider convention process. For scientists, a disputed or sensitive seabed area is not just a political headline. It can affect whether survey lines are approved, whether data can be shared, and whether a vessel is allowed to work there at all. This can lead to undersampling. If an area is politically complicated, scientifically interesting, and expensive to reach, it may simply not be visited often. Not because scientists are lazy or uninterested, but because every visit is a project. A sediment core in a legally simple area may take months to plan. A core in a sensitive area may take years, or may not happen at all. In the meantime, researchers use satellite data, existing reports, nearby stations, models, or indirect measurements. These can be valuable, but they are not perfect replacements. Invisible borders can therefore create invisible gaps in knowledge. The blank spaces on scientific maps may not be blank because nothing is there. They may be blank because getting permission to look properly is difficult. Military and security concerns can also affect timing. A research cruise may be delayed because of exercises, patrols, inspections, or regional tension. A drone survey may be refused near sensitive areas. Acoustic mapping may be restricted. A ship may be asked to keep away from a zone for reasons that are not fully explained. Scientists may not always know whether the reason is security, infrastructure, politics, or simply bureaucracy moving at the speed of a tired tortoise. The result is the same. The station is dropped from the plan, moved, or postponed. This is where avoidance becomes a very practical word. A team may avoid a region because the permit did not come through. It may avoid a station because a pipeline corridor crosses nearby. It may avoid a boundary area because the planned work could be misunderstood. It may avoid a mud volcano field because it lies close to active oil infrastructure. It may avoid a coastal zone because of a protected habitat, a fishing season, or a military restriction. None of these reasons is as dramatic as exploding methane or vanishing islands, but they are often more common. The world is full of places that are not physically impossible to study, only administratively difficult enough that researchers choose a safer or simpler alternative. This does not mean the Caspian is closed to science, far from it. Research is carried out by national institutes, regional projects, environmental programs, universities, energy companies, and international collaborations. The Tehran Convention process, Caspian environmental reporting, satellite monitoring, national surveys, and academic work all show that the sea is being studied. But the pattern of research is uneven. Some areas are easier to access because they are near ports, inside well-regulated national zones, or covered by existing partnerships. Other areas remain harder because they involve boundaries, industry, sensitive resources, or security rules. Science follows not only curiosity, but access. There is also the question of data. In many parts of the world, scientific data can be published openly after collection. In the Caspian, some data may be sensitive because it reveals seabed structure, resource potential, infrastructure location or environmental problems. Bathymetric maps, seismic profiles, pipeline routes, methane emissions, pollution records, and fish stock data can all have political or economic value. If data is sensitive, it may be difficult to obtain, share, or publish. A scientist may know that a measurement exists but may not be able to use it freely. Or they may collect data under an agreement that restricts how it can be released. This can slow understanding, and it can make outside observers think nobody is studying an area when, in reality, the data exists but is not public. That is frustrating, but it is also normal in strategically important waters. The Caspian is not only a natural system, it is a resource basin, a transport corridor, a border region, and a security space. The same maps that help scientists understand mud volcanoes may help engineers plan pipelines. The same methane data that helps climate scientists may affect energy reporting. The same seabed profiles that reveal geological hazards may reveal commercially valuable structures. The same fish survey that helps conservation may affect fishing limits. In a place where science touches money and sovereignty, access becomes careful. A useful way to picture this is to imagine the Caspian as a room shared by 5 households. In the middle of the room is a large table covered with food, tools, old stains, important papers, and a few delicate instruments. Everyone agrees the table matters. Everyone also has different claims to parts of it. Some items are shared, some are private, some are dangerous, and some are still being argued over. Now imagine a researcher walking in and saying, very politely, "I would like to scrape material from this corner, photograph that drawer, listen under the table and take a few samples home." The request may be reasonable, it may even be useful for everyone, but nobody is going to answer, "Of course, wander wherever you like." They're going to ask what, where, why, when, with whom, and who gets the results. This is why permits are not a side issue. They are part of the science. A permit can determine which season the work happens in, which stations are approved, what gear is allowed, whether samples can cross borders, whether foreign personnel can join, whether drones can fly, and whether the data can be published. A rejected permit can reshape an entire study. A delayed approval can push a cruise into worse weather. A condition attached to the permit can require local observers, shared data, restricted movement, or avoidance of certain coordinates. The final scientific paper may not show all of this. It may simply say, samples were collected at selected stations, which is the academic way of hiding 3 months of emails and several people slowly losing faith in calendars. There is also a safety benefit to this system, even when it feels slow. Authorities may know about hazards scientists do not. They may know which areas have active drilling, restricted navigation, unmarked structures, military activity, or recent incidents. Local agencies may have current charts and warnings. Energy operators may know where pipelines lie. Fishery authorities may know when sensitive species are present. Environmental agencies may know which sites are protected. A permit process can therefore prevent accidents. It can also ensure that local scientists are involved, which improves interpretation because people who work in the Caspian year after year understand details that a visiting team may miss. Still, the system can create blind spots. If sensitive areas are too hard to access, they may become less studied than safer areas. This can distort our understanding. Scientists may have good data from open or cooperative zones, and weaker data from disputed, restricted, or industrial zones. A map made from available measurements can look complete, but the missing stations may be exactly where the most important changes are happening. This is especially true for pollution, methane seepage, seabed deformation, and habitat loss. The hard-to-reach places are often hard to reach for a reason, and that reason may be scientifically relevant. The Caspian's invisible borders also shape how scientists talk. They may avoid strong claims if data coverage is uneven. They may say undersampled, data limited, poorly constrained, or requires further investigation. These phrases sound modest, and they are. They are also signals. They often mean that scientists suspect something important may be happening, but the available evidence does not yet allow certainty. In a politically complex sea, uncertainty can come not only from natural variability, but from access. The unknown is sometimes natural, sometimes it is administrative. Sometimes it is both, which is the scientific version of a locked drawer inside a foggy room. And yet this carefulness is not a failure. It is the only realistic way to study a place like the Caspian. The sea is shared. Its resources are valuable. Its ecosystems are under pressure. Its seabed is active. Its waters are changing. Its borders matter. A research vessel that ignores those facts would not be brave. It would be unserious. The best Caspian science respects the rules, works with local experts, uses remote sensing where direct access is difficult, and treats every approved station as part of a larger political and environmental system. So when scientists avoid certain waters, it may be because the boundary is invisible but real. It may be because written permission has not been granted. It may be because the area lies near oil and gas infrastructure, a security zone, a protected fishery, a disputed seabed, or a national sector where research must be coordinated carefully. It may be because the data would be sensitive. It may be because the science is better done indirectly at first, from satellites, aircraft, drones, or nearby stations. In the Caspian, caution is not only about mud, methane, or low oxygen. It is also about sovereignty. Above the water, these borders cannot be seen. From space, the Caspian appears as one connected body, long and dark, with pale shallows in the north and deeper water in the south. Satellites do not need passports. They do not ask permission to notice a coastline retreating, a sediment plume spreading, an oil slick shining, or a temporary island rising after a mud volcano eruption. And that is why, when ships stay away from certain parts of the Caspian, another kind of science often begins overhead, with sensors watching quietly from orbit. From space, the Caspian appears as one connected body, long and dark, with pale shallows in the north and deeper water in the south. Satellites do not need passports. They do not ask permission to notice a coastline retreating, a sediment plume spreading, an oil slick shining, or a temporary island rising after a mud volcano eruption. And that is why, When ships stay away from certain parts of the Caspian, another kind of science often begins overhead, with sensors watching quietly from orbit. There is something almost unfairly calm about a satellite image. From hundreds of kilometres above Earth, the hard parts of fieldwork vanish. No waves slap the hull. No winch jams at an inconvenient moment. No permit officer asks whether the sampling bottles are listed correctly on page 7. No one has to stand on a rolling deck in the dark, wondering if the thing making that noise is the pump, the cable, or the Caspian deciding to add a little suspense. A satellite simply passes over, gathers reflected light or radar signals, and continues on its path. But the image it leaves behind can show changes that would be difficult, dangerous, expensive, or politically awkward to observe from a ship. This is not because satellites are magical. They are not. They cannot taste the water. They cannot pick up a sediment core. They cannot tell a worried scientist whether the sample bottle cap was tightened properly. But they are extremely useful because they look often, they look widely, and they look without needing to enter the water at all. For a place like the Caspian, where some areas are shallow, industrial, restricted, remote, unstable, polluted, or simply hard to reach, this matters a great deal. Satellite remote sensing lets scientists ask the first questions from a safe distance. It does not replace field science, but it can show where field science is needed, where caution is justified, and where something has changed while everyone on the ground was busy arguing with logistics. One of the most obvious things satellites see is the shrinking shoreline. NASA's Earth Observatory used MODIS images from 2006 and 2022 to show how falling water levels exposed new dry land around the shallow northern Caspian. In the 2022 image, pale salt and mineral crusts appear along parts of the shoreline where water had retreated. NASA also notes that radar altimetry data from multiple satellites show Caspian water levels have been dropping since the mid-1990s, and that future decline could continue as warmer temperatures increase evaporation. That kind of view is very hard to get from a boat. A boat sees the local problem. A satellite sees the shape of the whole retreat. In the northern Caspian, where the water is shallow and the bottom slopes gently, even a modest fall in water level can move the shoreline a long way. Former water becomes mudflat. Mudflat becomes salt crust. A channel that once carried boats may become too shallow. A wetland may dry at the edges. A seal habitat or bird feeding area may shift. From space, these changes show up as colour, texture, exposed land, and altered water patterns. On the ground, they may show up as a stranded pier, a confused map, or a research vessel that can no longer reach last year's sampling station without scraping something expensive. This is one reason satellite monitoring is not just convenient. It is sometimes the only practical way to maintain continuity. If a coastline retreats over hundreds of kilometres, no one can walk every metre of it each season with a measuring tape, unless they have an alarming amount of free time and extremely durable shoes. Satellites can repeat the measurement again and again, showing how the coast changes over months, years, and decades. They can help scientists decide which areas are changing fastest and where field teams should go when they finally can. In a closed basin like the Caspian, where the water level responds to river inflow, evaporation, climate, and human water use, this wide view is essential. Satellites also see sediment. This may sound less dramatic than mud volcanoes or oil slicks, but sediment is one of the sea's main ways of leaving evidence. Around river mouths, especially near the Volga Delta in the north, water can turn green, tan, or milky, where sediment is carried into the sea or stirred from the shallow bottom. NASA's MODIS imagery shows sediments colouring the northern Caspian water in swirls of light green and tan, with the Volga River Delta visible nearby. Those colours are not decoration. They tell scientists about river discharge, erosion, currents, shallow water mixing, and the movement of fine material. Sediment matters because it carries more than minerals. It can carry nutrients, organic matter, pollutants, and traces of industrial or agricultural activity from far inland. It can bury contaminants, then release or move them again when disturbed. It can affect water clarity, which affects sunlight, which affects algae, which affects oxygen, which eventually affects deeper water chemistry. A sediment plume is a simple-looking feature with a long list of consequences. From a satellite, it may look like pale smoke spreading underwater. From a scientist's point of view, it is a moving map of what the land is sending into the sea. Satellites can also watch algal blooms, especially when the water surface changes colour or when specific wavelengths of light reveal high chlorophyll or cyanobacteria indicators. A study of cyanobacterial blooms in the southern Caspian used MODIS satellite imagery to examine cyanobacteria index, floating algae index, fluorescence line height, chlorophyll A, and sea surface temperature during bloom events. The researchers found that certain satellite products could help detect bloom conditions, while also noting that some methods were not sufficient on their own for offshore detection. That last part is important. Satellite science is powerful, but it is not automatic truth. A sensor sees light or radar backscatter. Scientists then interpret it. Watercolour can be affected by algae, sediment, dissolved organic matter, sunlight angle, cloud, haze, surface roughness and instrument limits. A green patch may be a bloom, but it may need confirmation. A dark radar feature may be oil, but it may also be calm water, wind shadow, biological film or another lookalike. Satellites are excellent witnesses, but even excellent witnesses need careful questioning. Oil slicks are a good example. Synthetic aperture radar, or SAR, is widely used to detect oil on the sea surface, because oil films can dampen small surface waves. That makes affected areas appear darker in radar imagery. Copernicus explains that oil spills appear on satellite SAR imagery as dark spots around an incident, and Sentinel radar data can help authorities detect and monitor the spread of oil. A Copernicus Sentinel-1 applications page also notes that oil slicks are distinctly visible in SAR imagery as characteristically dark features, and that oil detection can be used to gather evidence of illegal discharges, analyse spill spread, and identify natural seepage. In the Caspian, this is especially useful because the sea has oil production regions, natural hydrocarbon seepage, shipping routes, and mud volcano zones. A 2025 study mapped oil pollution on the Caspian Sea surface using satellite remote sensing data from 2022 to 2024. It used Sentinel-1A SAR imagery, Sentinel-2 multispectral imagery, and Landsat-8 and Landsat-9 optical data. The study focused on severe surface oil pollution regions, including natural seepage near Cape Safid Rud and the Chelikan Peninsula, the oil rocks production region, the South Caspian mud volcano cluster, and main shipping routes. That is exactly the kind of work that helps when ships stay away. A satellite can survey large areas repeatedly, including places where direct sampling would be difficult because of industry, border rules, shallow water, or safety concerns. It can show patterns. Are slicks appearing near shipping lanes? Are they recurring near natural seep zones? Are they linked to mud volcano activity? Do they change seasonally? Are they larger after storms or during calmer conditions? The 2025 study reported seasonal variability in the number of oil patches detected in visual images, variability in individual slick size, and a cumulative map of petroleum hydrocarbon pollution on the sea surface, including pollution from oil-containing water spills from ships. But this also shows why satellite observations must be handled carefully. A dark patch in a radar image may start the investigation, not finish it. In April 2024, Reuters reported a disagreement over satellite imagery near Kazakhstan's Kashagan oil field. An ecological organisation said Sentinel-1A images showed a slick of about 7 square kilometres, while the field operator denied a spill and said the imagery showed a different natural phenomenon. Local authorities said they planned visual inspection and sampling. That kind of disagreement is not a failure of satellite science. It is a reminder that satellite detections need validation, context, and sometimes physical samples. The image says, "Look here." It does not always say, "Here is the full legal and chemical explanation." This is especially true in the Caspian, where natural seepage and industrial pollution can resemble each other at first glance. A slick may come from a vessel discharge, a platform incident, a natural seep, a mud volcano, or something that only looks like oil. Wind matters, currents matter, sea state matters, radar angle matters, optical cloud cover matters. If the sea is too calm, SAR images can produce false dark areas. If the sea is too rough, small slicks may break up or become difficult to see. If clouds cover the scene, optical sensors may miss it entirely. Satellites are not sleepy, but they are still limited by physics. The ghost islands of the Caspian show another strength of satellite monitoring. In early 2023, the Kumani Bank mud volcano produced a temporary island about 25 kilometers off Azerbaijan's coast. NASA's Landsat 8 and Landsat 9 imagery showed that the volcano's crest was below the sea surface in November 2022. An island had appeared by February 14th, 2023, and by late 2024 only a much smaller portion was still visible above water. NASA reported that additional satellite observations suggested the island emerged between January 30th and February 4th, 2023, and measured about 400 meters across. That is the sort of event satellites are made to catch. A temporary island can appear offshore, change shape, and erode away before many people have a chance to study it directly. A ship may not be nearby. Weather may be poor. The area may require permission. The fresh mud may be unsafe to land on. But Landsat can record the before, during, and after. It can show the sediment plume trailing away from the island. It can show the island shrinking. It can help scientists connect a sudden surface feature to an underwater mud volcano eruption. It can also remind everyone updating nautical charts that the seafloor has been making edits again. NASA's account of the Kumani Bank event also notes that earlier eruptions there produced temporary islands, including one in 1861 and a larger one in 1950. The 2023 island fits that older pattern of short-lived landforms created by mud volcano activity. A research vessel might avoid the site immediately after such an eruption, because the new mud is unstable, gas may still be venting, and the seabed may have changed. A satellite does not solve those hazards, but it lets scientists observe the hazard without stepping on it, which is usually an underrated advantage. Satellites can also track the shape of mud volcano islands along the Absheron Peninsula. NASA described several tadpole-shaped islands in Azerbaijan that formed from explosive mud volcano eruptions and were later reshaped by erosion. Their tails likely formed as currents eroded weak mud deposits and redeposited sediment on the sheltered side. NASA also noted that Azerbaijan has one of the world's highest concentrations of mud volcanoes, including many underwater features in the South Caspian. For researchers, this means satellite images are not only snapshots. They are time-lapse records of how soft new land is built, cut apart and moved by water. That matters for navigation and risk. A mud volcano bank can become an island. An island can become a shallow. A shallow can vanish from the surface but remain dangerous for vessels. Erosion can move sediment into nearby water. Gas release may continue after the visible event ends. If scientists or survey vessels rely only on old maps, they may be surprised. Satellite imagery reduces that surprise by showing recent changes. It is not perfect, especially for submerged features, but it gives warning when the surface has changed enough to be seen from orbit. Then there is ship traffic. Satellites can see vessels directly in some radar images, and they can also support monitoring of routes where ship discharges may occur. In oil slick studies, repeated dark streaks along shipping lanes can point to possible illegal bilge water discharge or routine pollution patterns. The 2025 Caspian oil pollution mapping study specifically paid attention to anthropogenic pollution associated with discharge of oil-containing waters from vessels. That is important, because a research ship does not need to follow every vessel to know where suspicious patterns recur. The satellite can help identify where the sea surface repeatedly shows signs that deserve attention. But again, ships still matter. A satellite may identify a likely slick, but legal proof or chemical attribution may require sampling. A vessel may need to collect water, skim surface film, measure hydrocarbons, check wind and current conditions, or compare the slick with nearby ship tracks. A satellite helps narrow the search, which matters enormously in a sea as large as the Caspian. Without that first overhead clue, a field team might spend days looking at ordinary water and developing a personal grudge against the horizon. Satellites also help with temperature. Thermal sensors can track sea surface temperature patterns, showing warming, cooling, fronts, and areas where water masses meet. Surface temperature does not reveal everything below, but it helps interpret stratification, mixing, evaporation, and bloom risk. In the Caspian, where warmer air and evaporation are tied to declining water levels, surface temperature patterns matter. They can also show where shallow water heats quickly, where river plumes spread, and where seasonal changes may affect oxygen and biology. A ship can measure temperature very accurately along a line. A satellite can show the wider pattern on the same day. Still, the deeper Caspian reminds us of what satellites cannot see. They cannot directly measure oxygen at 500 meters. They cannot collect methane from bottom water. They cannot identify every buried contaminant. They cannot tell whether a sediment layer is toxic without samples. They cannot always see through clouds with optical sensors, and radar sees surface texture rather than chemistry. This is why satellite monitoring and fieldwork need each other. The satellite points, the ship tests, the lab confirms, the model connects. The next satellite pass checks whether the pattern continues. In difficult Caspian areas, this sequence can be slowed by access. A satellite may spot a suspicious slick near a restricted zone. Scientists may want samples, but permission takes time. A coastline may retreat rapidly near a sensitive habitat, but the site may be hard to reach by land or boat. A mud volcano island may appear, but direct landing may be unsafe. A bloom may develop offshore, but weather prevents field validation. So satellite evidence sometimes remains partly unconfirmed for longer than researchers would like. This does not make it useless. It makes it a clue waiting for the right conditions. There is a quiet tension here. Satellites see without entering, but they cannot fully understand without contact. Ships can collect the truth of water and mud, but they cannot always go where the question is. In the Caspian, that tension is not a minor detail. It is one of the main ways science is done. The most difficult areas are often watched first from above: a dangerous mud volcano field, an old oil zone, a shallow retreating coast, a suspected slick along a ship route, a bloom-prone southern region, a border area where direct research may take months of coordination. The satellite becomes the first visitor, the one that can pass overhead without disturbing anything. This has changed the meaning of avoidance. In the past, avoiding an area might have meant knowing very little about it. Today, a ship may avoid a place while satellites still build a record. Scientists can compare images from different years. They can map recurring slicks. They can follow shorelines. They can watch islands appear in a road. They can measure surface temperature. They can estimate bloom extent. They can see sediment after storms. They can identify areas where the next field expedition should focus. Avoidance no longer means blindness. It means using distance as part of the method. There is also something democratic about satellite images, at least compared with some forms of field data. Many Landsat, Sentinel and MODIS datasets are openly available. Researchers in different countries can examine the same shoreline or slick. Independent scientists can compare results. Environmental groups can raise concerns. Governments can verify or dispute claims. This does not remove politics, as the Kashagan example shows, but it changes the conversation. A patch of water that might once have gone unnoticed can now appear in a radar scene and become a question people must answer. That can be uncomfortable. Satellites can reveal change that is slow enough to deny locally but clear over decades. They can show a coastline retreating even when a harbour still functions. They can show repeated slicks even when no single event becomes famous. They can show sediment plumes after river floods, blooms after warm calm periods, and temporary islands that rise and vanish before most people ever hear about them. They do not care whether the result is convenient. They record what their sensors can record, with the blunt patience of machines. For scientists, the task is to turn those records into reliable knowledge. That means correcting images, removing clouds, accounting for wind, comparing sensors, validating with field data, and avoiding overstatement. A satellite image can be seductive because it looks complete. It is not complete. It is a surface view, a radar response, a colour pattern, a measurement of reflected or emitted energy. It becomes science only after careful processing and interpretation. The Caspian teaches this lesson very clearly. A dark slick may be oil or a lookalike. A green patch may be algae or sediment. A pale shoreline may be salt crust, dry mud, or exposed minerals. A missing island may have eroded, submerged, or simply fallen below the sensor's ability to detect it clearly. The image is the beginning of the sentence, not the full paragraph. And yet, without those images, the Caspian would be harder to understand. Ships cannot be everywhere. Permits do not arrive instantly. Dangerous places are not always available for direct study. Some areas are too shallow, too remote, too industrial, or too changeable for routine visits. Satellite monitoring gives researchers a way to keep watching, even when human presence is limited. It lets them see the scale of change before deciding where to risk closer work. So when ships stay away, satellites may still be keeping account. They see the northern shallows retreating and leaving pale mineral crust behind. They see sediment from rivers and stirred up lake beds spreading through shallow water. They see possible oil slicks near natural seeps, platforms and shipping routes. They see bloom conditions in warm surface water. They see mud volcano islands appear, shrink and vanish. They see patterns too wide for one vessel and too slow for one field season. They do not solve every Caspian mystery, but they stop many of those mysteries from remaining completely hidden. And this brings the journey back toward the reason scientists avoid certain parts in the first place. It is not because the Caspian is unknowable, it is because it has to be known carefully. Some places are better watched first from orbit. Some are better sampled only after the maps are updated. Some need permission before a hull crosses the invisible line. Some need a calm sea, a trained crew, and equipment that can handle gas, oil, mud, depth, or low oxygen. The Caspian does not refuse science. It simply does not reward careless science. By the time satellite images, field samples, legal permissions, and old maps are placed together, the picture becomes clearer, though not simple. The avoided places are not empty spaces. They are places where too many important things overlap. Geology, industry, borders, wildlife, pollution, climate, and water that has nowhere easy to go. And as we begin to settle the pieces into place, the final lesson is less about fear and more about respect. The quiet parts of the Caspian are not always safe, and the difficult parts are not always unreachable. They are places science approaches gently, with distance first, then instruments, then patience. The quiet parts of the Caspian are not always safe, and the difficult parts are not always unreachable. They are places science approaches gently, with distance first, then instruments, then patience. And perhaps that is the best way to understand the whole story. Scientists do not avoid certain parts of the Caspian Sea because the sea is filled with a single hidden danger. There is no one forbidden patch of water where all the answers sit waiting in the dark, tapping a little sign that says, "Please do not disturb." The truth is more practical and more interesting. Different parts of the Caspian ask for different kinds of caution. Some ask for geological caution. Some ask for chemical caution. Some ask for legal caution, some ask for environmental caution, some ask for the very ordinary caution of not taking a research vessel into shallow water that has recently changed its mind about being water at all. The Caspian is a place where many problems overlap. It is the world's largest inland body of water, but it has no natural outlet to the open ocean. Water comes in through rivers, especially the Volga, and then much of it leaves only through evaporation. That means salts, sediments, pollutants and long-term changes can stay inside the system in ways that make the sea different from an ordinary open coast. NASA has described the Caspian's shrinking shoreline and the role of evaporation and water loss, while researchers continue to warn that falling levels can expose wide areas of shallow seabed, especially in the north. That alone would make the Caspian difficult to study. A closed sea does not refresh itself easily. If a pollutant enters, it may not simply drift away into the wider ocean. If water levels fall, shallow habitats can retreat, ports can struggle, coastlines can change, and old maps can become less useful. The northern Caspian, with its broad, shallow shelf, is especially sensitive because small vertical changes can create large horizontal changes. A 1 metre fall in a steep basin may not change the shoreline much. A 1 metre fall across a shallow plain can reveal kilometres of mud and salt. That is not a mystery in the dramatic sense. It is geography doing what geography does, which is often inconvenient but rarely apologetic. Then there are the old oil fields and industrial areas. The Caspian, especially around Azerbaijan, has been tied to oil production for a very long time. Offshore platforms, pipelines, ports, old wells, natural seeps and industrial sediments all complicate research. A scientist looking at water quality may also have to think about what happened decades earlier. A geologist mapping the seabed may have to think about infrastructure. A team sampling mud may have to ask whether hydrocarbons in that mud came from natural seepage, old activity, recent leakage, ship traffic, or several sources combined. It is not enough to say, there is oil here. The Caspian asks the harder question, which oil, from where and when? That question matters because the Caspian's oil story is not separate from its natural geology. Mud volcanoes, methane seeps, and hydrocarbon-rich sediments belong to the region's deep structure. Azerbaijan has one of the world's largest concentrations of mud volcanoes, and NASA has reported that at least 140 underwater mud volcanoes occur in the South Caspian along Azerbaijan's coast. These are not ordinary hills underwater. They are places where gas, mud, fluids, and sometimes hydrocarbons move upward from below. Some are quiet, some erupt, some create temporary islands, some change the shape of the seabed. A research team can learn a great deal from them, but only by treating them as active systems rather than unusual scenery. And this is where the Caspian's calm surface becomes a little misleading. A person standing on the shore may see only water, light, wind, and perhaps a distant platform. A satellite may see a slick, a sediment plume, a shrinking coastline, or a new patch of land. A scientist lowering instruments through the water may discover methane, low oxygen, chemical layering, or soft sediment that behaves nothing like the firm bottom suggested by an old chart. The Caspian keeps reminding us that the surface is only one page of the document. The rest is below, and some of it is written in mud. Methane is one of those hidden pages. It can come from deep geological systems or from microbial processes. It can rise through vents, dissolve into water, feed microbes, collect in sediment, or escape into the atmosphere. Around mud volcanoes, it can also become a fire risk, because methane is flammable. That does not mean every seep is about to burst into flame. It means scientists need to know where gas is moving, how much is moving, and whether the source is natural or linked to human activity. In an oil-rich region, that distinction is not always simple. A methane plume near the Caspian may come from geology, industry, or both. That is why careful measurement matters more than dramatic guessing. Below all of that is the deeper water. The southern Caspian reaches depths of more than 1,000 meters, and deep water does not behave like surface water. It can become layered. It can mix slowly. It can lose oxygen as organic matter, and reduced compounds are broken down. Low oxygen does not make the deep sea a monster. It makes it chemically sensitive. It changes which organisms can live there, how nutrients cycle, how sediments behave, and how gases such as methane may be consumed or transported. Studying those depths requires proper vessels, calibrated sensors, long cables, careful sampling, and enough time to measure the water column properly. A single scoop from the surface will not tell the story of what is happening hundreds of meters below. Then come the borders. The Caspian is shared by Russia, Kazakhstan, Turkmenistan, Iran, and Azerbaijan, and research is shaped by national sectors, territorial waters, fishery zones, security concerns, and resource rights. The 2018 Convention on the Legal Status of the Caspian Sea created a framework for navigation, territorial waters, fishery zones, seabed use, and marine scientific research. The Convention text states that scientific research in certain areas and on certain resources requires written permission from the relevant coastal state, and that research may be suspended under conditions including security concerns. That is one of the main reasons a scientific blank spot on a map does not always mean a natural mystery. Sometimes it means the data is difficult to collect legally. Sometimes it means a permit was delayed. Sometimes it means the location is close to a pipeline, an oil field, a military area, a protected fishery, or a politically sensitive seabed zone. A research vessel does not travel like a thought. It travels under a flag with equipment, crew, permissions, responsibilities, and consequences. The water may look open, but the rules are real. This is why satellites have become so valuable. They can monitor the Caspian without crossing a maritime boundary in the same way a ship does. They can watch shorelines retreat, mud volcano islands appear and vanish, sediment plumes spread, and possible oil slicks form on the surface. They cannot replace field work because they cannot collect bottom water, test sediment chemistry, or confirm every surface signal. But they can point to places that need attention and help scientists decide where fieldwork is worth the risk, cost, and paperwork. When ships stay away, satellites can keep the first watch. The Caspian also has a regional environmental framework. The Tehran Convention, signed by the 5 Caspian states, is described by UNEP as the first legally binding regional agreement, signed by all Caspian littoral states for protection of the sea and its marine environment. That matters because the Caspian's problems are not owned neatly by one shoreline. Rivers cross regions, pollution moves, fish migrate, seals do not carry passports, a falling sea level affects ports, wetlands, oil infrastructure, fisheries, and coastal communities. Environmental protection in a closed basin has to be cooperative, or at least it has to try very hard to become cooperative, which is sometimes the most that international agreements can ask of human beings before lunch. So when people ask why scientists still avoid certain parts of the Caspian Sea, the answer is not fear. It is caution built from evidence. They avoid some places because the seabed may be unstable. They avoid others because old oil infrastructure may lie below. They avoid some areas because methane may be venting. They avoid some because oxygen-poor water or contaminated sediment requires special methods. They avoid some because permissions are not in place. They avoid some because the sea level has changed, the route is too shallow, or the weather does not allow safe work. And sometimes they avoid a place directly while still studying it indirectly, through satellites, models, historical records, and nearby measurements. That is not failure. That is how careful science works. Science is not always a person in a white coat making a bold discovery in a neat laboratory. Sometimes science is a ship not entering a zone because the maps are uncertain. Sometimes it is a team waiting for written permission. Sometimes it is a satellite image being compared with one from last year. Sometimes it is a muddy sample being sealed before gas escapes. Sometimes it is a researcher deciding that the best measurement is the one taken safely tomorrow, not recklessly today. There is something reassuring in that. The Caspian is not being ignored simply because parts of it are difficult. It is being approached with tools that match the difficulty. Satellites for wide views, drones for dangerous gas zones, ships for direct sampling, local partnerships for legal and practical access, chemical tests for pollution, acoustic surveys for seabed shape, long-term monitoring for changes that do not reveal themselves in a single season. Each method is incomplete by itself, but together they make the sea a little less unknown. And still, there will be places that resist easy understanding. A mud volcano may remain quiet for years and then erupt. A temporary island may appear and vanish before many people see it. A slick may be detected from orbit but require sampling before anyone can say what caused it. A deep oxygen layer may change slowly enough that only long records reveal the trend. A restricted area may be scientifically important but hard to enter. The Caspian does not offer all its answers at once. It gives them in pieces, often with conditions attached. That may be frustrating, but it also makes the sea scientifically important. Places that are easy to study are useful, of course, but places that are difficult often teach us the most about how nature, industry, law and climate interact. The Caspian is not a remote wilderness untouched by people, and it is not only an industrial waterway. It is both natural and human-shaped. It has rare species and old pollution, deep basins and busy ports, mud volcanoes and satellite tracks, oil platforms and changing wetlands. It is a real place, which means it is complicated in the way real places usually are. Perhaps that is the quiet lesson at the end of this journey. Avoidance is not always distance. Sometimes avoidance is respect. It is the decision to watch before entering, to ask permission before sampling, to test carefully before claiming certainty, and to remember that a calm surface can hide active processes below. The scientists who avoid certain Caspian waters are not turning away from knowledge. They are choosing the slower route toward it. And now, after moving across this inland sea from its closed basin to its old oil fields, from mud volcanoes to methane, from deep oxygen-poor layers to invisible borders and satellite eyes, we return to the surface for a moment. Imagine the Caspian at night. Not as a warning sign, not as a forbidden place, but as a wide body of dark water holding many different histories at once. River water from the north, salt left behind by evaporation, sediment from distant landscapes, traces of industry, gas from deep underground, signals from living things, coordinates written into law, images recorded from space. A research vessel may sit at the edge of one of those difficult areas, engines low, instruments ready, waiting for weather, permission or morning light. Nobody needs to whisper dramatically. Nobody needs to point at the horizon as if a sea monster is expected at any moment. The caution is quieter than that. It is found in the checklist, the chart, the gas sensor, the permit folder, the satellite image, and the decision to move carefully. And maybe that is a good thought to rest with. Not every mystery needs to be rushed. Some places are understood better when we stop treating caution as weakness. The Caspian shows that science can be curious without being careless. It can be patient without being passive. It can stand at the edge of uncertain water and say, "Not yet," while still preparing to learn. So, dear listener, we have come to the end of our slow crossing. We began with a sea that is not quite a sea in the usual sense, and we found a place where water, mud, gas, oil, law, and climate all meet in one enclosed basin. We saw why scientists may keep their distance from certain parts, not because those places are imaginary danger zones, but because they are real, active, sensitive, and sometimes difficult to enter safely. And as you settle more deeply into the quiet around you, I would love to ask what I asked at the beginning in a slightly different way. Are you listening near water tonight, or far from it? Is there a river, lake, coast, canal, or rain-soaked street somewhere near you? Water has a way of making places feel still, even when they're changing all the time. The Caspian reminds us of that. Still on the surface does not mean still underneath. If this gentle journey gave you something calm to think about, or helped the day loosen its grip a little, I would be very grateful if you liked the video, subscribed, and shared this quiet space with someone who enjoys science at a slower pace. It helps more people find these long, sleepy journeys into the strange edges of the world. For now, let the Caspian fade back into darkness. Let the ships grow small. Let the satellites pass silently overhead. Let the mud settle, the bubbles rise, the deep water rest in its heavy layers, and the shoreline hold its complicated shape for one more night. Science will return to the difficult places when it can, with better maps, steadier tools, and the patience those places require. Sleep well, fellow traveller, wherever you are listening from, and whatever quiet water is nearest to you tonight.